Hello, and welcome to The Sleepy Scientist. Tonight we're going to drift into the soft folds of space itself. Not the kind of space filled with socks under the bed or missing keys in the couch cushions, but the vast, silent, curving space that stretches between galaxies. The kind that might loop, stretch, or fold in ways our minds can barely grasp. Perfect bedtime material. Now I should warn you, this video might be just a little too interesting. If it keeps you awake, I'm truly sorry. But if you do end up wide-eyed at 3 a.m. contemplating the topology of a toroidal universe, well, at least you'll have some great material for your next existential daydream or breakfast conversation. Before we curl up into the curvature of space-time, I'd love it if you gave this video a gentle like, or even subscribed if you haven't already. It helps this sleepy little corner of the internet grow. And if you feel like sharing, let me know in the comments where in the world you're listening from and what time it is where you are. I imagine some of you are already in bed, while others are brushing teeth or gently winding down with a cat on your chest and a cup of tea in hand. Wherever and whenever you are, I'm glad you're here. Now, take a deep breath, settle in, and prepare to explore the geometry of everything, from flat, open and closed universes to strange cosmic shapes that might just loop back on themselves. And finally, just a gentle reminder, this video is for relaxation and educational purposes only. It's not intended to be medical advice or a substitute for sleep treatment. If you're having trouble sleeping regularly, please do speak with a healthcare professional. Now then, let's begin. What is shape, really? It seems like a simple question at first. We spend our lives surrounded by shapes. Triangles on street signs, circles on clocks, squares on screens. A child learns their shapes before they even learn to tie their shoes. We point at things and say that's round, or that's sharp, or that looks kind of like a potato, and we all nod, satisfied that we understand. But once we step outside the cosy world of dinner plates and traffic cones into the boundless stretch of the universe, things get much more peculiar. Because out there, beyond the clouds, beyond the stars, beyond even the most distant galaxies, there are no corners to count, no edges to trace with a ruler. Space itself is not made of stuff you can hold or bend. It's not sitting on anything. It doesn't wrap around something larger. And yet, it has a shape. The question of shape in a cosmic sense isn't about what space is made of, but how it behaves. In mathematics, shape isn't only about what you see. It's about relationships, how angles connect, how surfaces curve, how lines behave when they go on forever. Shapes can be hard-edged or fluid, visible or purely theoretical. And when we talk about the shape of the universe, we're not talking about its decoration. We're talking about its fundamental structure. To understand that, let's rewind a few thousand years, back when our ancestors first began looking up at the sky and wondering about their place in the world. Long before anyone had equations or telescopes, humans were already obsessed with shapes. They carved circles into stone, aligned monuments with the movements of the sun, and noticed that the moon always kept the same face turned toward the earth. These observations weren't just about beauty or curiosity. They were about survival. Seasons, harvests, tides. Many of life's essentials came in cycles, and cycles meant patterns, and patterns meant shapes. Geometry, which literally means earth measure, was born not in the halls of physics departments, but in fields and farms. Ancient Egyptians used it to re-establish property lines after the Nile flooded. Babylonians mapped the stars in grids. The Greeks, of course, took things further. Euclid, often called the father of geometry, lived over 2,000 years ago and built an entire mathematical system from a handful of simple truths. He assumed, for example, that a straight line was the shortest distance between 2 points, and that parallel lines never touch. For centuries, Euclidean geometry ruled the world. It described everything from pyramids to planetary orbits with neat logic and satisfying clarity. But eventually cracks started to form, metaphorically, not geometrically. People began to wonder, What if those parallel lines did meet? What if space didn't behave the way we expected, especially on vast cosmic scales? In the 19th century, mathematicians like Gauss, Lobachevsky and Riemann began to play with the idea that space could bend and twist. They imagined geometries where triangles didn't add up to 180 degrees and where you could travel in a straight line and return to where you started, without ever turning. These weren't just thought experiments. They were the foundations of non-Euclidean geometry, where shape was no longer confined to flatness and familiar angles. Then came Einstein. When Albert Einstein published his theory of general relativity in the early 20th century, he transformed the idea of shape from something static into something dynamic. According to his theory, mass and energy don't just exist in space, they shape it. Gravity isn't a force pulling objects together, but the result of space itself curving around mass. Planets orbit the sun not because they're being yanked by some invisible thread, but because the sun's mass bends the fabric of space-time, and the planets are simply following the curve. Suddenly, shape became not just a mathematical abstraction, but a physical reality. The universe wasn't a fixed backdrop. It was more like a stretchy, flexible canvas. Galaxies, stars, black holes, they all press into that canvas, creating valleys and dips that guide motion. Even light follows these curves. In fact, we can see distant galaxies distorted and stretched, because their light passes through warped regions of space on the way to our telescopes. It's called gravitational lensing, and it's a real-world demonstration that shape, in the cosmic sense, isn't just theoretical, it's observable. But here's where it gets really mind-bending. We're not just talking about the shape of things in the universe, we're talking about the shape of the universe itself. That's like trying to describe the shape of the stage when you're standing on it, unable to see its full extent or even whether it has an edge at all. Can something be flat and infinite, curved and finite, looping back on itself like a cosmic racetrack? To answer that, scientists had to dig deeper. They needed a way to define shape that didn't rely on standing outside of the universe and looking in, because, well, there is no outside. Everything we know, everything we measure, is from inside the system. And yet, by examining how light travels, how galaxies move, and how the oldest radiation in the universe spreads out, we can begin to piece together a picture of that hidden geometry. Physicists describe this using terms like curvature and topology. Curvature tells us how space bends, whether it's flat, positively curved like a sphere, or negatively curved like a saddle. Topology, on the other hand, tells us how space is connected. You could have a flat universe that loops back on itself like a video game map, or a curved one that stretches forever. The two properties, curvature and topology, aren't always the same, and they each shape our understanding of reality in different ways. This brings us to one of the most beautiful ideas in all of science, that shape is not always visible. You might live your whole life in a space that loops, curls, or bends, and never notice. The paths you take, the angles you measure, the stars you observe, they could all behave as if the universe is flat, even if it secretly wraps around itself on a scale far beyond your reach. It's a little like being a bug on a balloon. If you're tiny enough, the surface feels flat. You can draw straight lines, build little houses, and never suspect that you're actually walking in a giant circle, only by carefully measuring those paths, or watching how light behaves across vast distances, could you start to suspect the truth, that what feels flat may actually be curved, and that in the end is what makes shape such a slippery, wonderful thing. It's not just about appearance, it's about structure, it's about how space behaves. And when we talk about the shape of the universe, we're really asking, what kind of stage are we all dancing on? Whether it's flat, curved, infinite, finite, looped, or lumpy, the shape of the cosmos quietly governs everything, from the path of comets to the fate of galaxies. And though we may never see its full form, every measurement, every equation, and every starlit night brings us a little closer to tracing its invisible lines. So the next time you think about shape, You might find it hiding not just in triangles and circles, but in the vast, silent contours of reality itself. Let's take a moment to consider something a little strange. The geometry of absolutely nothing. Not nothing as in a tidy, uncluttered desk or an empty cereal box, but the real deal. Empty space. Pure, silent, invisible nothingness. No stars, no planets, no atoms. Just the vacuum of space, stretching out in every direction. It might seem odd to say that nothing could have a shape. After all, shapes are for things. Rocks, teapots, pineapples. But in physics, even the nothingness between things can be shaped. In fact, it must be. Let's start with something a bit more familiar. Picture a flat piece of paper. That's a pretty good stand-in for what ancient mathematicians thought space was like. Flat, infinite, and well-behaved. You draw a triangle, and the angles always add up to 180 degrees. Two parallel lines will never meet, no matter how far you extend them. This is what we call Euclidean geometry, named after Euclid, the ancient Greek mathematician who basically invented geometry as a formal system. He laid down 5 postulates, simple rules that defined how lines and shapes behave. For over 2,000 years, those rules described the only kind of space anyone could imagine. But there was one postulate that always made mathematicians a little uneasy. The 5th one, often called the parallel postulate, says that if you draw a line and pick a point off that line, you can draw exactly one line through that point that never meets the first line. That sounds simple, but it's actually quite delicate. It works beautifully on flat paper, but what if the surface you're drawing on isn't flat? Suppose you're on the surface of a sphere, say, a globe. If you try to draw straight lines, known in math as geodesics, you'll find that things get weird. Lines that start off parallel eventually meet. For example, lines of longitude on Earth are all technically parallel at the equator, but they converge at the poles. On a curved surface, the rules change. The angles of a triangle can add up to more than 180 degrees. Suddenly, Euclid's system doesn't apply. In the 19th century, mathematicians like Nikolai Lobachevsky, Janos Bolyai, and Carl Friedrich Gauss began to explore these non-Euclidean worlds. They developed entire systems of geometry based on curved surfaces, positive curvature, like the sphere, and negative curvature, like a saddle. These new geometries weren't just bizarre thought experiments. They were self-consistent, logical, and just as mathematically valid as Euclid's. It was a shocking discovery at the time. There isn't just one kind of geometry, there are many. This opened the door to a radical idea. If geometry could be curved, maybe space itself could be curved too. Maybe the nothingness between objects wasn't flat and featureless, but flexible and dynamic. It just needed someone to connect the dots. Enter Albert Einstein. In the early 20th century, Einstein developed general relativity, a theory that redefined gravity not as a force, but as a geometric feature of space-time. According to this theory, massive objects like stars and planets don't simply sit in space, they bend it. They create dips and curves in the fabric of space-time itself, and other objects follow these curves. That's what gravity is, not a pull, but a path. Imagine placing a heavy bowling ball on a trampoline. It sinks into the fabric, creating a well. Now roll a marble across the surface. The marble curves around the depression, not because the bowling ball is pulling on it directly, but because the surface itself is curved. That's an analogy, of course, but a useful one. In Einstein's universe, space and time are fused into a 4-dimensional fabric, and massive objects reshape that fabric wherever they go. This means that even empty space, the vacuum, the nothingness, is not just a passive stage, it's an active participant. If space can curve, then it can stretch, ripple, and twist. In other words, it has geometry, even when there's nothing in it. We see the consequences of this in many surprising ways. One of the most elegant is the bending of light. If light travels through curved space, it too will follow a curved path. We can observe this when light from distant galaxies passes near a massive object. like a cluster of galaxies or a black hole. The light bends around the object and reaches us from multiple angles. This effect, known as gravitational lensing, is like watching distant galaxies through a giant cosmic magnifying glass, and it proves, beyond any philosophical doubt, that space itself has structure. Another curious thing about curved space is that it changes how we understand distance and time. In a curved universe, the shortest path between 2 points isn't always a straight line, at least not as we draw it on paper. Instead, it's a geodesic, the natural path that follows the curvature of space. If you've ever flown on an airplane and noticed that your flight path curves northward before descending again, you've experienced this in 2 dimensions. It looks longer on the map, but it's actually the shortest path across the curved surface of the Earth. Now imagine doing that in 3 dimensions, or more accurately in 4 if we include time. The geometry of nothing affects how we move, how we fall, even how we age. Clocks tick differently in curved regions of space-time. This is not science fiction. It's something we've tested with satellites and atomic clocks. GPS systems, for example, have to account for the effects of both velocity and gravity on time. Without corrections from Einstein's equations, your phone's location would be off by several kilometers every day. Even more remarkable is that this flexible geometry isn't just shaped by stars and planets. It can exist even in deep empty space, regions far from any matter. The shape of that emptiness is determined by the overall structure of the universe itself. Scientists talk about spatial curvature as a large-scale property. Is the universe flat, curved like a sphere, or saddle-shaped? This isn't just a mathematical curiosity. It affects how the universe expands, how galaxies cluster, and what fate awaits the cosmos in the distant future. But wait, how do we even know what the shape of empty space is? After all, we can't exactly float above the universe and take a photo of it. Instead, scientists look at light, lots and lots of light. In particular, the light from the cosmic microwave background, the oldest light in the universe, which has been travelling through space for nearly 14 billion years. By studying tiny fluctuations in this light, researchers can measure how it has stretched and bent across billions of light years. These measurements tell us that, on the largest scales we can observe, the universe appears to be very nearly flat, but not perfectly so. Of course, there's a catch. We can only see so far. Our view is limited by the speed of light and the age of the universe. Beyond that horizon could be more of the same, or something entirely different. The shape of space may shift beyond what we can ever measure. It may be flat here and curved there. It may loop, twist, or ripple in higher dimensions. We simply don't know. And that's part of what makes the geometry of nothing so captivating. It challenges our instincts. We like to think of empty space as absence, as the void, the silence between stars. But in reality, space is active. It has properties. It can bend, flex, and even vibrate with gravitational waves, which are ripples in space-time that travel at the speed of light. We detected these for the first time in 2015, when 2 black holes collided over 1 billion light-years away and sent tremors through the cosmos, gently wiggling our detectors on Earth. Space itself shook. That's the geometry of nothing at work. It may seem like an odd phrase, but the more we study it, the more we realize there's no such thing as truly empty space. Even nothing has shape. Even nothing has rules. And in the vast, quiet universe, that shapeless-looking nothing turns out to be one of the most structured things of all. Let's begin with a quiet thought. Imagine you're floating in deep space, far from any planet or star. No up, no down, no wind, no sound. Just you, the silence, and the stars. Now imagine you drop a marble from your hand. What does it do? If you're far from any gravitational pull, it just floats there. But if you're near Earth, that marble will drift gently downward, not because something invisible is tugging on it with ghostly fingers, but because the very space around Earth is shaped in such a way that the marble naturally moves in that direction. This is the heart of one of the most beautiful ideas in physics, Gravity is not a force, it's a curve. This was Einstein's great revelation. Before him, we had Isaac Newton, who gave us a very successful recipe for how gravity works. According to Newton, gravity was a force that any object with mass exerts on any other object with mass. The more massive the object and the closer it is, the stronger the pull. It worked perfectly well for apples falling from trees, for cannonballs, and for the orbits of planets. But Newton didn't explain what gravity was, just how it behaved. He even admitted as much, saying he didn't feign hypotheses about its true nature. Then, in the early 20th century, along came Albert Einstein, hair askew and equations swirling. He dared to ask, what is gravity really? And he found his answer not in force but in geometry. In Einstein's universe, space and time are not separate things. They're fused together into a single entity called space-time. This fabric isn't passive, it's dynamic. It bends, stretches and ripples, and most importantly it's shaped by energy and mass. Anything with mass deforms the fabric around it. Think of space-time as a stretchy, invisible mattress. Place a bowling ball in the centre, and the surface sags. Now roll a marble across the mattress. It curves around the dip, not because the ball reached out and grabbed it, but because the marble is simply following the contours of the surface. That's how planets orbit stars, how moons orbit planets, and how your feet stay planted on Earth. Einstein's theory of general relativity, published in 1915, redefined gravity as the warping of space-time by mass and energy. His equations are complex, but their consequences are elegant. Instead of a force pulling objects together, objects move along the curved paths created by space-time itself. Even light, which has no mass, follows these curves. One of the earliest and most striking confirmations of Einstein's theory came during a solar eclipse in 1919. British astronomer Arthur Eddington led an expedition to measure the position of stars near the sun's edge during the eclipse. The idea was that if Einstein was right, the sun's mass would bend the light from those stars, making them appear slightly out of place. And that's exactly what happened. The starlight bent. Not by a lot, but by just the right amount predicted by Einstein's equations. It was front-page news. Overnight, Einstein became a global celebrity, and the universe quietly reshaped itself in the public imagination. This bending of light by gravity isn't just a neat party trick. It's something we see in space all the time. Massive objects like galaxies or clusters of galaxies can act as gravitational lenses, bending and magnifying the light from even more distant galaxies behind them. These lenses allow us to peer deeper into space than we ever could otherwise, seeing galaxies from the early universe that would otherwise be too faint to detect. It's cosmic optics on the grandest scale. But general relativity doesn't stop at bending light. It also tells us that time itself is affected by gravity. Clocks run slower in stronger gravitational fields. This is called gravitational time dilation, and though it sounds like science fiction, we've measured it. Place two ultra-precise atomic clocks at different altitudes, say, one on a mountain and one at sea level, and over time they'll fall out of sync. The one closer to Earth's centre, where gravity is stronger, ticks ever so slightly slower. If you've ever used GPS, you've benefited from this insight. The satellites that make GPS possible orbit high above Earth, where gravity is weaker and time runs just a bit faster than it does down here. If engineers didn't account for both gravitational time dilation and the effects of special relativity, which deals with the speed of the satellites, your phone's location could be off by several kilometers. Einstein may not have had Google Maps in mind when he developed general relativity, but without him, it wouldn't work. Perhaps one of the most dramatic predictions of general relativity is the existence of black holes, regions of space where the warping of space-time becomes so extreme that nothing, not even light, can escape. Black holes were once thought to be mathematical curiosities, but now we know they are real, and they are out there, lurking in the centres of galaxies and spinning invisibly through space. In 2019, we even captured an image of one, a blurry glowing ring surrounding a shadowy void. It was like seeing Einstein's equations come to life. More recently, in 2015, scientists announced the first detection of gravitational waves, ripples in the fabric of space-time caused by massive objects like black holes colliding. These waves stretch and squeeze space itself as they pass by, and detecting them required instruments so sensitive they could measure distortion smaller than a proton. The very idea that space could ripple like water still feels astonishing. But we've now detected many such events, each one a kind of cosmic chime from the universe's most extreme cataclysms. All of this, the bending of light, the slowing of time, the orbiting of planets, the existence of black holes and gravitational waves, comes from a single idea, that mass and energy tell space-time how to curve, and curved space-time tells objects how to move. It's a neat little loop, and it works with stunning precision. And yet, despite its successes, general relativity isn't the whole story. At very small scales, inside atoms for instance, it doesn't mesh well with quantum mechanics, our other great theory of nature. Trying to unify these two frameworks remains one of the biggest puzzles in modern physics, but that doesn't diminish what general relativity has achieved. It remains one of the most beautiful and successful scientific theories ever devised. There's something deeply poetic about it too. The idea that gravity is not a tug but a tilt, that the universe is shaped not by strings and pulleys, but by elegant curves and invisible waves, is both humbling and awe-inspiring. We live our entire lives under the influence of these curves. We sleep, wake, walk, and dream while space-time gently cradles us in its invisible hands. And most of the time, we don't even notice. Gravity, for all its might, is silent. It has no colour, no taste, no smell. It doesn't hum or buzz, but it shapes everything. From the arc of a thrown stone to the motion of galaxies, it is the quiet geometry behind all movement. Einstein gave us the tools to see that, to understand the world not just as a collection of forces, but as a graceful, curving dance of space and time. And in that vision, even nothing becomes something. Even silence has structure. And the invisible becomes the architecture of reality itself. When most people hear the word flat, they probably think of a pancake, a piece of paper, or that one tire that always lets you down when you're running late. But in cosmology, flat has a much more fascinating meaning, one that could reveal the very architecture of the universe. The question of whether space is flat, curved inward like a sphere, or curved outward like a saddle, is one of the most profound in physics. It shapes how we think about everything from the Big Bang to the fate of the cosmos. Let's begin with the basics. Imagine a triangle. On a flat surface, like a sheet of paper, if you draw a triangle and measure the angles, they'll always add up to 180 degrees. That's a hallmark of flat, or Euclidean geometry. Now imagine doing the same on the surface of a sphere like a globe. You can draw a triangle with three 90-degree angles, say, from the equator to the North Pole and back again. And suddenly, the sum is 270 degrees. That's not flat geometry anymore. That's positive curvature. On the flip side, imagine a saddle shape. If you draw a triangle there, the angles will add up to less than 180 degrees. That's negative curvature. Now take these simple ideas and scale them up, way, way up. Instead of measuring triangles on paper or globes, imagine drawing them between galaxies, using beams of light as your lines. That's essentially what cosmologists do. By examining the paths light takes over billions of light years and how distant objects appear to us, we can infer whether space is flat, curved inward, or curved outward. But what do we actually mean by these three shapes in a cosmic sense? A flat universe means that parallel lines stay parallel forever. It also means the rules of Euclidean geometry hold up even at cosmic distances. Triangles still add up to 180 degrees, and light travels in straight lines that aren't warped by the curvature of space, except, of course, when it passes near massive objects like stars or black holes, which create local distortions. On the whole, though, flat space is the vanilla flavour of the cosmos, simple, infinite and perfectly balanced. A closed universe, on the other hand, has positive curvature. It's like the surface of a sphere, but in 3 dimensions. In this model, if you travel far enough in one direction, you could, hypothetically, end up back where you started, without ever turning around. It's a finite universe, but one with no edges. There's no outer wall to bump into, no void beyond the boundary, just a loop, closed upon itself. This type of universe could eventually stop expanding and start contracting, leading to a big crunch scenario, a reversal of the Big Bang. Then there's the open universe, which has negative curvature. Picture an infinite saddle that stretches in all directions. It never loops, never closes, and just keeps going forever. This model suggests a universe that will expand forever, growing colder and emptier over time. Galaxies will drift apart, stars will burn out, and in the far future, even atoms may decay into silence. Each of these shapes isn't just a matter of geometry. They have profound implications for how the universe behaves and what its future might look like. But here's the tricky part. How do you measure something as enormous as the shape of the entire universe? You can't exactly fly out to the cosmic edge with a measuring tape and check whether space bends. Fortunately, the universe has left us some clues, and one of the biggest is light. In particular, the light from the cosmic microwave background, the afterglow of the Big Bang, offers a snapshot of the universe when it was only about 380,000 years old. This light has been travelling through space ever since, stretching and shifting as the universe expands. When we observe this ancient radiation, we see patterns, tiny fluctuations in temperature and density that tell us how matter was distributed in the early cosmos. By measuring the angular size of these fluctuations, scientists can determine whether space is flat or curved. If the universe is flat, those patterns appear at a certain expected size. If space is positively curved, the light paths converge and the fluctuations look larger. If it's negatively curved, the light paths diverge and the fluctuations look smaller. It's a bit like looking at a chessboard through different lenses. Curved ones stretch or shrink the pattern, while a flat lens keeps it unchanged. These measurements are incredibly precise. Thanks to data from satellites like COBE, WMAP, and the more recent Planck mission, we know that the universe appears to be very nearly flat. But here's the catch. It's only flat within our observable horizon. Beyond that, we simply don't know. The universe could still curve at scales larger than we can see. It could loop, ripple, or twist in ways forever beyond our detection. Our cosmic map is vast, but it still has edges. What's even more remarkable is that this flatness isn't just some cosmic coincidence. In fact, the early universe had to be astonishingly well balanced for space to appear so flat today. If the universe had even a tiny bit too much energy density, it would have quickly curved inward and collapsed. Too little, and it would have flown apart too quickly for stars and galaxies to form. This precise balance is known as the flatness problem, and it puzzled physicists for years. One elegant solution is the theory of cosmic inflation. This idea suggests that in the first tiny fraction of a second after the Big Bang, the universe expanded faster than the speed of light, not violating relativity, because space itself was expanding. This rapid inflation smoothed out any wrinkles or curves, flattening the universe like steam pressing a shirt. It's like blowing up a balloon so large that any tiny curve on the surface becomes invisible to someone standing on it. Inflation not only explains the flatness of space, but also the uniformity we see across the cosmos, even in regions that seem too far apart to have ever communicated. Still, even with these insights, the shape of the universe remains one of the biggest mysteries in cosmology. Is it perfectly flat? Just nearly flat? Is there a subtle curve we haven't yet detected? Or could space have a strange topology? looped or folded in ways that mimic flatness at smaller scales. And what about edges? People often wonder whether the universe has a boundary, but in curved geometry, boundaries aren't always necessary. A two-dimensional creature living on the surface of a sphere wouldn't encounter an edge. They would just keep walking and eventually circle back. Likewise, a closed universe has no edge but is still finite. Meanwhile, a flat or open universe could be infinite, with no center, no boundary, and no place you could call the end. This all makes flatness sound deceptively simple. But flat space is still a vast and mysterious thing. It could stretch forever. It could hide strange topological twists. It could even be part of a multiverse, one of many patches of space-time with different curvatures or dimensions. In the end, asking whether space is flat is like asking what kind of canvas the universe is painted on. And the answer, as far as we can tell, is a nearly flat one stretching into darkness, whispering subtle clues about its shape in the light of ancient stars. Whether it loops, curves, or stretches beyond imagination, space holds its shape in silence, waiting patiently for us to measure its angles and ask again what it all means. Let's take a deep breath and imagine, just for a moment, that everything around you is getting farther away. Not in a panicked, "Where did I leave my wallet?" sort of way, but calmly, steadily, silently. The chair beneath you, the stars above, the space between galaxies, it's all stretching. Not because things are flying apart through space, but because space itself is expanding. This isn't science fiction. It's one of the most extraordinary facts about our universe. The cosmic stage we're standing on is growing. But what does that really mean, and how do we know it? The story begins nearly 14 billion years ago with the Big Bang. Contrary to how it's often portrayed, the Big Bang wasn't an explosion in space. It was the rapid expansion of space itself. There was no outside for it to explode into, and no center where the bang occurred. Instead, every point in the universe began expanding away from every other point, like a loaf of raisin bread rising in the oven. The raisins, standing in for galaxies, move apart not because they're propelling themselves outward, but because the dough around them is stretching. This idea was first hinted at in the early 20th century, when astronomer Edwin Hubble observed that distant galaxies were moving away from us. Not only that, but the farther away they were, the faster they seemed to be receding. This discovery, now known as Hubble's law, was a game changer. It meant the universe was not static, as many had believed, but dynamic. Something was causing the vast distances between galaxies to grow. So what was going on? It turns out that the very fabric of space can stretch. Space is not a static backdrop like a cosmic wallpaper. It's a flexible, evolving structure. And general relativity, Einstein's revolutionary theory, allows for such stretching. His equations describe how the geometry of space and time evolves over time in the presence of energy and matter. When applied to the universe as a whole, they predict a changing cosmos, either expanding or contracting. The expanding model quickly became the front-runner, especially once cosmic microwave background radiation was discovered in the 1960s. This ancient light, left over from the early universe, is a faint glow that fills all of space. It's a bit like the thermal aftershocks of the Big Bang, a gentle cosmic hum in the background. The fact that this light is still around, and that it has been stretched into longer and cooler wavelengths over time, is compelling evidence that the universe has been expanding for billions of years. A popular analogy to explain this is the balloon metaphor. Picture the universe as the surface of a balloon. Now draw a few tiny dots on it to represent galaxies. As the balloon inflates, the dots move farther apart, not because the dots themselves are moving, but because the surface they sit on is stretching. The key is that every dot sees every other dot moving away. There is no special center, no edge, just expansion happening equally everywhere. This analogy helps explain a few tricky ideas at once. First, there's no edge to the universe. at least not in any conventional sense. The surface of a balloon doesn't have an edge for a two-dimensional creature living on it. It's finite but unbounded. Second, no matter where you are in the universe, it looks like you're at the centre of expansion. That's not because you're special, but because everything is moving apart in all directions. Now here's a question people often ask. If the universe is expanding, why aren't we? Shouldn't your body, your house, and your sandwich be stretching too? Happily, no. You're safe from cosmic inflation, at least at the personal scale. That's because expansion only dominates on very large scales, where the pull of gravity, electromagnetism, and nuclear forces are too weak to resist. Your atoms, molecules, and muscles are all tightly bound by forces much stronger than the gentle stretching of space. The Earth isn't expanding, the solar system isn't expanding, even our galaxy isn't expanding. The universe's growth only becomes noticeable when you zoom out far enough, hundreds of millions of light years, where galaxies themselves are not gravitationally bound to one another. Think of it this way. If the universe were a giant sponge slowly swelling in water, your body is like a chunk of iron embedded in the sponge. Local structures resist the stretch, but the sponge as a whole still grows. Another question that tickles the brain: what is the universe expanding into? This is where the balloon metaphor can be a bit misleading. While the surface of a balloon expands into the air around it, our universe isn't expanding into anything. Space itself is growing. There's no external space it's spilling into, just more space being created between things. From a mathematical point of view, the coordinates describing the universe are stretching. It's not that galaxies are flying through space like shrapnel from an explosion. They're staying where they are while space swells around them. This expansion also affects how we see distant galaxies. Light travelling through expanding space gets redshifted. Its wavelength stretches out, making it appear redder and less energetic. The more distant a galaxy is, the more its light has been redshifted by the time it reaches us. In fact, some galaxies are so far away that the space between us and them is expanding faster than the speed of light. That doesn't violate any laws of physics because it's space itself expanding, not objects moving through space. This means there are regions of the universe we will never see. Their light will never reach us, no matter how long we wait, because the space between us is stretching too fast. These unreachable areas form what's called the cosmic event horizon, a kind of ultimate limit on what's observable. It's a humbling thought. Not only is the universe expanding, but parts of it are vanishing beyond our view forever. And yet, in the grand theatre of the cosmos, this expansion tells us something profound. The geometry of the universe, the way space curves, the way time unfolds, is not frozen in place. It evolves, it stretches, it carries the past forward, one expanding moment at a time, and we're all passengers on this gently growing stage. One of the most mind-bending discoveries in recent decades is that this expansion is actually accelerating. In the late 1990s, astronomers observing distant supernovae noticed that these exploding stars were fainter than expected, not because they were farther away due to normal expansion, but because the universe had been speeding up. Something was pushing galaxies apart faster and faster over time. This mysterious driver of expansion has been dubbed dark energy, and it currently makes up about 70% of the total energy content of the universe. We don't know exactly what it is. It doesn't clump, it doesn't emit light, and it seems to act like a constant pressure woven into the fabric of space-time. Whatever it is, it's making the universe balloon more rapidly with each passing moment. As the expansion continues, distant galaxies will eventually slip out of sight. In tens of billions of years, observers in our galaxy, if any remain, might see only the faint glow of nearby stars, unaware that the universe ever had billions of others. The sky could go dark, not from nightfall, but from cosmic solitude. But for now, we are fortunate. We live in a time when we can still see the echoes of the Big Bang, still trace the patterns of galaxies, and still measure the stretch marks of space itself. The universe is expanding, and with each measurement we're learning to read its shape, written not in stone, but in the stars. Imagine a universe as flat as a pancake, though in this case there's no syrup, no plate, and definitely no edge to fall off. Just an endless, smooth expanse stretching in every direction, quietly going about its cosmic business. That's the idea behind a zero-curvature universe, a cosmos so geometrically well behaved that it might make even Euclid nod in approval. In this kind of universe, the rules of geometry behave just as we expect them to from our middle school math class. Triangles always have angles that add up to 180 degrees. Parallel lines, if perfectly drawn, never intersect, not even after crossing billions of light years. Circles have the same relationship between diameter and circumference no matter where you draw them. And a straight line really is the shortest distance between 2 points. It's the gold standard of flatness. No bulges, no warps, no saddle-like dips. Just clean, crisp, infinite space. But what does it mean for an entire universe to be flat? First, it's worth clearing up a small misconception. When cosmologists say flat, they don't mean two-dimensional, like a sheet of paper. A flat universe is still three-dimensional: length, width, and height. What makes it flat is its curvature, or more specifically, its lack of curvature. Imagine walking across a room in a straight line. In a flat universe, you can keep walking forever without curving back toward where you started, or drifting subtly away from your original path due to warped geometry. Your path remains straight, forever. It's space behaving like an infinite floor, not like the surface of a sphere or a saddle. So how do scientists determine whether the universe is actually flat? After all, we can't exactly stretch a cosmic ruler from one galaxy to another and check for bends. Instead, we look at how light travels across the universe, specifically how it stretches and spreads over billions of years. One of the most powerful tools we have for this is the cosmic microwave background, the faint afterglow of the Big Bang. This ancient light has been travelling through space for nearly 14 billion years, carrying with it clues about the shape of everything it's passed through. By analysing the size and distribution of tiny temperature fluctuations in this light, scientists can test whether space is curved. Here's how it works. If the universe is flat, light from these distant fluctuations travels in straight lines, and the patterns appear at predictable sizes. If space is positively curved, like a sphere, the light converges a bit, making the patterns appear larger. If space is negatively curved, like a saddle, the light diverges, and the patterns appear smaller. Thanks to data from missions like WMAP and Planck, we've measured these patterns with extraordinary precision, and the result? The universe appears to be very nearly flat. But nearly flat is not the same as perfectly flat. The universe could be incredibly close to zero curvature without quite getting there, like a pancake so vast that any slight curve is imperceptible, even across billions of light years. Or perhaps it's exactly flat down to the finest decimal, in a kind of cosmic balancing act that stretches from one end of time to the other. If it is perfectly flat, it implies something extraordinary. A flat universe doesn't just mean tidy geometry. It also hints at a very specific amount of energy and mass. In cosmology, this is called the critical density, the precise balance point between too much matter, which would cause the universe to eventually collapse, and too little, which would allow it to expand forever. A flat universe sits delicately between these two extremes. It expands forever, but more and more slowly, approaching a kind of cosmic cruising speed. Interestingly, when scientists first calculated the amount of matter and energy in the universe, they found only about 5% of what was needed for flatness. That included everything we could see: stars, gas, dust, planets, even black holes. Not nearly enough. But then came dark matter, an invisible form of matter detected only through its gravitational pull. That added another 27% or so to the tally. Still short. The rest. It turns out the remaining 68% appears to be made of something even stranger: dark energy, a mysterious pressure woven into the fabric of space itself, pushing galaxies apart and accelerating expansion. Put all of that together, ordinary matter, and dark energy, and the total density of the universe seems to land almost exactly at the critical value for flatness. It's a bit like throwing a dart blindfolded and hitting the bullseye from 1,000 miles away. This uncanny balance is one of the great puzzles in cosmology. Why should the universe be so precisely flat? Coincidence? Design? A deeper law of physics we haven't yet discovered? One possible explanation is cosmic inflation, a theory that suggests the universe underwent a brief but incredibly rapid expansion in its earliest moments. During this split second, any initial curvature would have been smoothed out, just like blowing up a balloon until any tiny bumps or dents disappear. Inflation is a bit like a cosmic iron, flattening space-time into a near-perfect sheet. If this theory is right, it could explain why the universe looks so flat today, even if it didn't start that way. But let's step back from the math and the mystery for a moment. What would it feel like to live in a flat universe? The funny answer is, you already do, at least as far as we can tell. Everything we observe, from the orbits of planets to the shape of galaxies to the path of ancient light, behaves just as it should in a flat universe. Unless you're conducting incredibly precise cosmological experiments, you'd never notice anything unusual. There are no visual cues that space is curved, no strange warping at the edges of your vision, no point where you suddenly find yourself walking in a circle while trying to go straight. Flat space feels normal, and yet the implications are anything but ordinary. In a truly flat universe, space could be infinite. You could keep travelling in a straight line forever, never doubling back, never hitting an edge. There's no centre, no boundary, no preferred direction. It's symmetry writ large. That alone is a powerful statement, a kind of cosmic egalitarianism, where every point is just as good as any other. Or perhaps the universe only appears flat within the limits of what we can see. Beyond our observable horizon, space might gently curve in ways we'll never detect. It might even loop back on itself in a flat but finite topology, like a cosmic video game map where leaving on one side brings you back on the other. Whatever the case, the flatness of the universe remains one of the most compelling clues in our quest to understand reality. It tells us that space is not just a passive container for stars and galaxies, but an active structure with measurable properties. Geometry isn't just a tool for architects and artists, it's the foundation of existence. In the end, a perfectly flat universe may sound a little dull. No dramatic curves, no looping paths, no theatrical collapses. But in its simplicity lies a profound elegance, a universe where straight lines stay straight, where shapes behave and where the quiet order of geometry holds steady across unfathomable distances. It's not just flat as a pancake, it's flat as the laws of physics will allow. Imagine walking in a perfectly straight line for a very, very long time. You pass galaxies, nebulae, cosmic dust, the occasional confused comet, and just when you're certain you'll keep going forever, you end up back where you started without ever turning around. That's the strange but wonderful possibility offered by a closed universe. In this kind of universe, space is positively curved, meaning it bends like the surface of a sphere, not a saddle or a sheet. It's one of the three classic shapes cosmologists consider when trying to describe the geometry of the cosmos: flat, open, and closed. And the closed universe is the one that feels a little like cosmic origami, curved in on itself, looping without edges, without borders, and without a centre. Now, to be clear, we're not talking about the universe being shaped like a beach ball floating in some larger space. The analogy helps us visualize things, but we're dealing with three-dimensional space, curving in a higher dimensional way, which is something our brains didn't evolve to picture easily. But with a little imagination, it's not impossible. Let's start with a simpler version: the surface of a two-dimensional sphere. If you're a flat creature living on the surface of a balloon, you can walk in any direction and never encounter a wall or an edge. You can keep going indefinitely, and eventually you'll find yourself back where you began. The surface has no boundaries, but it's still finite. There's only so much area. Now imagine that same concept, but in 3 dimensions where the universe loops in all directions, not just around a surface, but through volume. This is what a closed universe could be like. Finite but unbounded. It doesn't go on forever, but there's no place where it stops. You'd never hit a wall, fall off the edge, or float into the void. Instead, space would gently curve back on itself. You might think of it like a hall of mirrors that loops endlessly. Not because the mirrors are playing tricks, but because the space itself curves your path. From a geometry perspective, this positive curvature changes how shapes behave. Triangles have angle sums greater than 180 degrees. Straight lines, technically called geodesics, eventually return to their starting points, and parallel lines, they don't stay parallel, they eventually meet. On a cosmic scale, these changes aren't just mathematical curiosities. They alter how light travels, how galaxies are distributed, and even how the universe evolves over time. But where does this curvature come from? In general relativity, the shape of the universe is determined by its energy density, essentially how much stuff is in it, including matter, radiation, dark matter, and dark energy. If the total density is higher than a specific critical value, space curves inward, forming a closed geometry. In a closed universe, gravity is strong enough to eventually slow expansion and reverse it. Over time, the universe could stop stretching and begin to contract, leading to a possible scenario known as the Big Crunch, where everything collapses back into a hot, dense point, perhaps to start the cycle again. Whether or not the universe will actually end this way is still an open question, but the closed model makes it possible, and it paints a poetic picture. A universe born in fire, expanding for billions of years, then cooling, pausing, and finally collapsing back into silence. What's fascinating is that you wouldn't necessarily feel any of this curvature in your everyday life. You don't float slightly uphill in one direction, or notice objects behaving oddly when you walk through your living room. On small scales, say, inside galaxies or solar systems, the curvature is negligible. It's only when you start connecting points across hundreds of millions or even billions of light years that the shape becomes apparent. So how do cosmologists look for clues? One method involves studying the cosmic microwave background, the ancient light left over from the Big Bang. This light acts like a snapshot of the early universe, frozen in time just 380,000 years after its birth. Scientists analyse the angular size of tiny temperature fluctuations in this background radiation. If the universe is closed, these fluctuations appear slightly larger than they would in a flat universe, because light paths converge as they move through curved space. Another method involves the distribution of galaxies on the larger scales. In a closed universe, the way galaxies are clustered and how their light is redshifted, stretched by the expansion of space, can give hints about the geometry. If we observe patterns that suggest convergence, just like those triangle angles growing too large, it could be a sign that we're inside a curved cosmos. The most recent measurements, particularly from the Planck satellite, suggest that the universe is very close to flat, but there's still a little wiggle room for positive curvature. Some analyses even hint, ever so slightly, at a closed universe. But the margin is tiny, and the uncertainties are real. It's like trying to tell whether the Earth is perfectly round by standing in your backyard and squinting at the horizon. You need very precise tools, and even then you're still stuck with only a limited view. There's another curious thing about closed universes. They can support multiple paths between 2 points. That means you could, in theory, shine a flashlight in one direction, and if you waited long enough, the light could loop around the universe and hit you from behind. Like mailing a postcard to yourself by tossing it into orbit. Of course, the actual travel time would be measured in billions of years, so it's not exactly a practical method of communication, but it's a delightful thought. This looping nature also opens up questions about the topology of the universe, its global structure. Could space be shaped like a three-sphere, a three-dimensional analogue of the surface of a regular sphere? Or might it be something even more exotic, like a Poincaré dodecahedral space, where space loops in intricate repeating patterns? These ideas are not just theoretical toys. Some cosmologists believe subtle patterns in the cosmic microwave background might hint at such hidden topologies, though the evidence remains elusive. If we really do live in a closed universe, it might offer some comfort. In an infinite universe, you can always wonder if something lies beyond. But in a closed one, there is no beyond. Every direction eventually brings you back. It's a complete cosmos, self-contained and elegantly curved, a place where the story of everything is written not on a boundless scroll but on a cosmic sphere. It might sound a little claustrophobic, this idea of a finite universe, but it's not. There's still room for an unimaginable number of stars, galaxies, and wonders. Finite doesn't mean small, it just means that the cosmos wraps around itself, gently bending the rules of geometry into a loop. And even if we never prove beyond all doubt that our universe is closed, the possibility offers a beautiful reminder. That space isn't just a void. It has shape, it has character, and it might just be gently curving beneath our feet, whispering across billions of light years that all paths eventually circle home. Let's go somewhere vast, not just big or really big, but endlessly big, and then some. Picture a universe that stretches in every direction, never loops, never curves back, and never even thinks about calling it a day. A universe that expands not into something, but into itself, forever. That's the unsettling yet oddly beautiful vision offered by the open universe, a cosmos shaped not like a balloon or a pancake, but like a saddle that never ends. This is a universe with negative curvature. That might sound a bit gloomy, but in geometric terms it simply means the rules of space are bent in the opposite direction of a sphere. Instead of curving inward like the surface of a globe, space curves outward, like the seat of an old wooden saddle, dipping down in one direction and arching up in another. It's called hyperbolic geometry, and it changes the way space behaves in quiet but powerful ways. Let's start with the basics. In an open universe, triangles act a little strangely. If you draw a triangle with 3 straight lines, what mathematicians call geodesics, the angles will add up to less than 180 degrees. The bigger the triangle, the greater the discrepancy. Parallel lines don't stay the same distance apart. They diverge over time. And if you were to draw a circle and measure its circumference, you'd find it was larger than expected based on its radius. In short, everything stretches out just a little more than your intuition says it should. But what does that mean on a cosmic scale? In the open universe model, space doesn't wrap around itself. There are no closed loops, no secret shortcuts, no paths that eventually bring you home. Instead, space extends infinitely in every direction. You could travel in a straight line for eternity and never cross your own path. Not because you're going in circles, but because there's simply too much room to ever run out of it. This type of geometry arises when the total energy density of the universe is less than a specific critical value. That includes all the matter, radiation, dark matter, and dark energy added together. If the density is too low to slow down cosmic expansion in a meaningful way, the universe ends up with negative curvature. There's not enough gravity to ever bring the expansion to a halt, let alone reverse it. Instead, the universe expands forever, cooling, dimming, and becoming ever more diffuse. It's a quiet, haunting picture. Over billions and trillions of years, galaxies drift farther and farther apart. The stars exhaust their fuel and fade to black. The matter left behind, cold husks of stars, drifting planets, and the occasional stubborn black hole, spreads thinner and thinner. Eventually the night sky might go completely dark, not because anything exploded or ended, but because everything simply drifted out of view, That's the ultimate fate of an open universe, a slow, graceful fade into the void. But how would we know if we live in such a place? Once again, cosmologists turn to the ancient light of the cosmic microwave background, the leftover glow from the Big Bang. By studying how this light spreads, and how its tiny temperature fluctuations appear across the sky, scientists can infer the geometry of space. In an open universe, these fluctuations appear smaller than expected. The light has travelled along diverging paths, spreading out more than it would in flat or positively curved space. Observations from satellites like WMAP and Planck suggest that the universe is very nearly flat, with only a tiny margin for error. That means the open model, while still a contender, is not the current favourite. But it's far from ruled out. There's still a chance, however slim, that our universe does in fact have a touch of negative curvature. The saddle shape might be subtle, stretched across such an enormous scale that we only notice it in the most delicate measurements. And then there's the matter of topology. Even an open universe could have a complex, twisted global structure. While negative curvature means infinite extent in the traditional model, some variations could involve strange shapes, multi-connected, wraparound structures that mimic infinity in clever ways. Think of space as a video game map that repeats, but not quite like you'd expect. These ideas are speculative, but they add a layer of delightful weirdness to an already strange concept. One thing that sets an open universe apart is its relentless expansion. In this model, the universe doesn't just drift apart, it accelerates into emptiness. And once that expansion gets going, it doesn't stop. Galaxies recede from one another at ever-increasing speeds. Eventually they become so far apart that light from one can no longer reach the other. Communication becomes impossible, observation becomes impossible. Each galaxy becomes an isolated island, alone in a sea of expanding darkness. Now, that might sound a bit bleak, but there's another way to look at it. An open universe is limitless. It offers infinite potential for discovery, for exploration, and for thought. Every direction is a path you haven't taken. Every patch of sky is a doorway to the unknown. In a saddle-shaped cosmos, the universe doesn't cradle you gently in a curved loop. It challenges you to step into the infinite, to keep moving forward without end. And there's something comforting in the consistency of it. No hidden loops, no unexpected returns, just straight lines, diverging paths, and a clean, honest geometry. It's the universe as an open road, not a maze. Some might find that lonely. Others might find it exhilarating. Interestingly, negative curvature also plays a role in mathematics and art. Hyperbolic space has fascinated artists like M.C. Escher, who used it to create intricate, repeating patterns that shrink toward infinity. In nature, hyperbolic shapes appear in coral, lettuce, and the delicate lacework of sea slugs. Even in our everyday world, the geometry of the saddle shows up in places you wouldn't expect, like Pringles, which yes are technically hyperbolic paraboloids. Back in the cosmos, the open universe also has implications for time. In this model, time stretches endlessly forward, never cycling back. There's no big crunch waiting at the end of the line, just more time, more space, and more questions. Physicists describe this as a cold death or heat death scenario, where entropy reaches its maximum, and the universe becomes a calm, uniform void. It's not a dramatic ending, more like the universe slowly falling asleep. Even if our universe isn't open, the very idea of it expands our imagination. It reminds us that space isn't necessarily bound or curved in friendly ways. It can be wild, vast, and uncaring of our need for closure. It can stretch beyond what we can see or even imagine, and it may never stop stretching. The open universe is like a story with no final chapter, just pages drifting into the unknown. It's infinite in scope, rich with mathematical mystery and quietly humbling. In a cosmos shaped like a saddle, the journey is never over, and for all its emptiness, it offers something truly profound: the freedom of forever, written into the very shape of space. If you could hold a telescope so powerful it peered into the deepest past, you'd eventually see something astonishing. Not the edge of the universe, but its beginning. Or at least a kind of cosmic fossil record of it. A faint, ancient glow. Not bright like starlight, but cold and gentle. It's been travelling through space for over 13.8 billion years, and it's still here, softly bathing the universe. This is the cosmic microwave background, or CMB for short, and it's one of the most important clues we have about the shape and story of everything. Imagine a photograph, not of your family or your dog wearing sunglasses, but of the entire universe, as a baby. The CMB is just that, a portrait of the cosmos when it was only about 380,000 years old, which, on a cosmic timeline, is practically its newborn stage. It's a snapshot of a moment when the universe transitioned from a hot, dense, opaque fog into something transparent and open. Before this point, the universe was filled with a searing plasma of particles and photons constantly colliding. Light couldn't get very far without being scattered like headlights in a thick fog. But then, something miraculous happened. The universe cooled down enough for protons and electrons to combine into neutral atoms. This process, called recombination, allowed light to finally move freely. Those newly liberated photons have been travelling through space ever since, stretching out into microwave wavelengths as the universe expanded, and today we can detect that ancient glow with specially tuned instruments. Now, if you could see the CMB with your eyes, the entire sky would glow faintly in all directions. It's not a bright glow, it's just a few degrees above absolute zero. But it's everywhere, and it's astonishingly uniform. In fact, for a long time that uniformity was a bit of a puzzle. The CMB is smooth to within a few parts in 100,000. But it's those tiny variations, those tiny temperature wrinkles, that hold the secrets to the shape of space itself. These minute fluctuations represent slight differences in density in the early universe. Regions that were just a little bit denser than their surroundings would eventually grow into galaxies, clusters, and cosmic structures. Think of them as the seeds of everything we see today, from spiraling galaxies to sleepy planets. And by mapping these fluctuations across the sky, we can learn an incredible amount about the geometry of the universe. Here's how it works. Imagine drawing a triangle on the sky, using the light from 3 distant points in the CMB. The shape and angles of that triangle will behave differently depending on the curvature of the universe. If space is flat, the angles will add up to 180 degrees, just like in normal geometry. If space is positively curved like a sphere, the triangle's angles will add up to more than 180 degrees, and if space is negatively curved like a saddle, they'll add up to less. Now, we can't exactly take out a giant protractor and measure triangle angles across the cosmos, but we can do something similar. Scientists study the angular size of temperature fluctuations in the CMB. There's a characteristic size, about 1 degree across, that corresponds to the distance sound waves could have travelled in the early universe before recombination. This scale is like a standard ruler imprinted on the sky. If the universe is flat, we see this ruler at its actual size. If the universe is curved, we see it distorted. And what have the measurements shown? Thanks to satellites like COBE, WMAP, and especially Planck, we've mapped the CMB in exquisite detail. These missions collected data over many years, producing all sky maps of the microwave background with remarkable precision. And when scientists analysed the angular sizes of the fluctuations, they found something extraordinary. The patterns match those expected from a nearly flat universe. Not a perfect pancake, perhaps, but very close. This doesn't mean the universe is exactly flat, there's still a tiny margin of uncertainty. But it does suggest that on the largest observable scales, space doesn't curve dramatically one way or the other. If the universe is curved, the curvature is so gentle that it escapes our current instruments. It might be like standing on a football field and trying to determine whether the Earth curves beneath you. Technically, yes, but practically it feels flat. The cosmic microwave background also provides other vital information. For instance, it helps us determine the proportions of the universe's contents. From the way the temperature fluctuations are distributed, we've been able to figure out how much of the universe is made of ordinary matter, just under 5%, how much is dark matter, around 27%, and how much is made of that mysterious stuff called dark energy, about 68%. These numbers matter because the total energy density of the universe is what determines its geometry. If there's too much, space curves inward. Too little, and it curves outward. But if the total density is just right, if all the ingredients add up perfectly, the universe ends up flat. And the CMB, by measuring the tiny bumps and dips in that ancient light, tells us that the balance is astonishingly close. It's a bit like baking a cosmic cake and finding that, against all odds, all the ingredients were measured perfectly, even the dark energy, which we still don't fully understand. Some physicists find this unsettling. Why should everything add up so neatly? One proposed explanation is inflation, a theory that suggests the universe underwent a period of rapid, exponential expansion in its first tiny fraction of a second. This would have smoothed out any initial curvature, leaving the universe looking flat, even if it wasn't perfectly balanced to begin with. But beyond the numbers, the CMB remains an emotional kind of miracle. These photons have been journeying across space since long before Earth formed, before the sun lit up, before even the first galaxies came into being. And yet they're still with us, quietly delivering a message from the dawn of time. When we tune our instruments just right, we hear that message, not in words, but in patterns, in fluctuations, in the tiniest variations in temperature ever recorded. It's easy to forget how remarkable this is. The universe has no obligation to reveal its secrets, and yet in the faint glow of the CMB, it has left behind a map not of cities and borders, but of sound waves rippling through plasma, a map drawn in light that has stretched for over 13 billion years across a stage that itself has grown larger with every passing second. This light doesn't flicker, it doesn't pulse, it simply is, everywhere, all the time. Every square inch of sky carries it, and yet it's so faint that only the most sensitive detectors can see it. It's like the softest whisper from the farthest past still echoing through the cosmos. And in that whisper, we find hints about everything. The shape of space, the ingredients of the universe, and even its possible future. We can never visit the early universe, not in person, but through the CMB, we have a window, cold, silent, and incredibly ancient, into the very moment the cosmos became visible. It's hard not to feel a little awe in that. After all, we're reading a message written in light older than stars, a message that tells us not just where we are, but what kind of stage we stand on. Whether it's flat, curved, or infinite, the universe left us clues, and they were glowing there the whole time. There's something oddly satisfying about triangles. Maybe it's their simplicity. Just 3 sides, 3 angles, and yet an entire world of geometry tucked into that tiny shape. Even ancient civilizations understood their power. The Egyptians used them to build pyramids. The Greeks used them to prove elegant theorems. And today, physicists use them to measure something vastly more ambitious. The shape of the entire universe. Yes, really. In a cosmos that stretches billions of light years in every direction, we're still using triangles to figure out where we stand. It's geometry class, just on a scale no high school whiteboard could ever contain. Let's start with a reminder. In flat 2-dimensional space, the kind we learn about in early math lessons, the angles of any triangle add up to exactly 180 degrees. This is one of those rules we treat as an unshakable truth, but it's only true if space is flat. Once space starts curving, triangles start acting differently. On a sphere, for example, you can draw a triangle with 3 90-degree angles. That adds up to 270 degrees. Try that on a chalkboard and your math teacher might faint, but on a globe, it's perfectly valid. This happens because spherical surfaces have positive curvature. They bend outward, like the surface of Earth. On the other hand, imagine a saddle. The surface curves down in one direction and up in another. If you try to draw a triangle there, the angles will add up to less than 180 degrees. That's negative curvature. The triangle spreads out more than usual, and the rules you once trusted shift subtly under your feet. Now imagine trying to draw a triangle on the universe itself. Not a tiny triangle you could sketch with a pencil, but a cosmic triangle, billions of light years across. One side might stretch between two distant galaxies. The other sides might follow the paths of light rays moving through space. It sounds wild, but this is exactly the kind of thing cosmologists do, and the results can reveal the universe's overall shape. The logic is beautifully simple. If the angles of a large triangle add up to more than 180 degrees, space is positively curved, like a sphere. If they add up to less, it's negatively curved, like a saddle. And if they add up to exactly 180 degrees, space is flat. This is known as the geometrical curvature of the universe, and it's one of the key questions in modern cosmology. But how do you actually make such a triangle? You can't use a cosmic protractor. Instead, astronomers turn to a much more elegant tool, light. Specifically, light from the cosmic microwave background, or CMB, the afterglow of the Big Bang. The CMB is full of tiny temperature fluctuations. These are areas of slightly higher or lower density that existed in the early universe. Scientists know the approximate physical size of these fluctuations because they correspond to sound waves rippling through the primordial plasma before light was able to travel freely. This known distance acts like a standard ruler, a fixed length we can use to gauge the shape of space. Here's where the triangle comes in. Imagine one side of the triangle being the distance between two of these ancient ripples. The second side is the beam of light travelling from those points to our telescopes here on Earth. The third side is formed by the angle between the light paths as we observe them in the sky. If the universe is flat, those light paths travel in straight lines, and the angle we measure matches the expected size of the fluctuation. If the universe is positively curved, space bends those paths inward, making the features appear larger than expected. If it's negatively curved, the light paths diverge and the features appear smaller. This test, measuring the apparent angular size of the known physical features, is sometimes called angular diameter distance measurement, and it's a powerful way to test curvature. The CMB gives us an entire sky full of such triangles ready for analysis. What have we found? Observations from missions like COBE, WMAP, and Planck have provided incredibly precise data. And the angles in our cosmic triangles, they seem to add up almost perfectly. The fluctuations appear just the right size to match a flat universe. Not curved like a sphere, not spread like a saddle, but flat. Or at least very, very close to it. That's not to say we've ruled out curvature entirely. There's still a small margin of uncertainty, about 1% or less. On cosmic scales, that's a hair's breadth. But it means the curvature, if it exists, is so subtle that it takes some of the most sensitive instruments in human history to even detect a hint of it. Of course, light doesn't just travel through empty space. Along the way, it passes through regions with different densities, clusters of galaxies, voids, dark matter fields. These all bend and distort the light slightly, a process known as gravitational lensing. So to measure those triangles accurately, cosmologists have to account for these tiny distortions. It's a bit like trying to read a road sign through heat waves on a summer day. The message is still there, but it wiggles a bit on the way to your eyes. Despite the complexity, this triangle test remains one of the cleanest ways to understand the geometry of space. It's a reminder that sometimes the oldest tools are still the most powerful. You don't need particle accelerators the size of countries to ask big questions. Sometimes a triangle will do. And triangles aren't just useful in the CMB, they also help us understand distances in other parts of cosmology. By comparing brightness and redshift of certain types of supernovae, for example, astronomers can estimate how far away they are and how fast the universe is expanding. These measurements too can be translated into geometric information about space's shape. In fact, combining multiple types of triangle-like measurements, like paths from the CMB, distances from supernovas and clustering of galaxies, gives us a more complete picture. It's like building a puzzle where each triangle is a piece. The more pieces we add, the clearer the picture becomes. And what a picture it is. We're talking about geometry at the grandest scale imaginable, not just the shape of a mountain or a continent, but the shape of reality. Whether space bends, loops, or stretches forever. Whether the universe is infinite or finite. Whether light can travel in circles or vanish into the void. And to think it all comes back to triangles. It's hard not to smile at the quiet elegance of it. The same shape used to build bridges and pyramids is also used to understand the universe itself. The same math we use to measure rooms and rooftops is written into the fabric of space-time. The universe may be vast, ancient and mysterious, but it's also surprisingly cooperative when it comes to math. So the next time you see a triangle, on a sign, in a logo, or hidden in a spiderweb, take a moment to appreciate it. Somewhere out there, a triangle older than galaxies is helping us measure the curvature of space. And somewhere, across the silent stretch of the cosmos, another one is waiting to be discovered. Picture a coffee cup and a donut. Not in a cafe, not in your kitchen, just as pure shapes. To a topologist, someone who studies the mathematical properties of space, these two objects are actually the same. Not because you can drink from a donut or eat your coffee cup, but because from a topological point of view they both have a single whole. If you could stretch and bend one without tearing or gluing, you could reshape the coffee cup into a donut and vice versa. That's topology, geometry without rulers, where the focus isn't on distances or angles but on how things are connected. And when it comes to the universe, topology might hold some of the most fascinating and mind-bending secrets of all. Most of the time, when we talk about the shape of the universe, we're discussing its curvature, whether space is flat, positively curved like a sphere, or negatively curved like a saddle. But topology goes deeper. It asks a more subtle question. How is space connected? Could it loop back on itself? Could you travel in a straight line forever and end up where you started, not because space is curved like a balloon, but because space is stitched together in a clever hidden way? In a topological sense, the universe could be like a video game screen where going off one edge makes you reappear on the opposite side. You keep walking forward, and without ever turning around, you arrive back where you began. That's not curvature, that's connection. A flat universe could still loop. An infinite-looking universe could actually be finite, just cleverly folded. Let's try a simple example, a two-dimensional square. Imagine an ant crawling on this square. If you identify, or glue, the left and right edges together, the ant now walks on a cylinder. Keep going and also glue the top and bottom edges, and you've turned the square into a torus, a donut shape. But from the ant's point of view, it's still crawling on flat land. The curvature hasn't changed, angles behave normally, but the topology is now different. The ant can keep walking straight, and eventually return to where it started. The surface is finite but has no boundary. Now scale that up to 3 dimensions. Could our universe be the 3-dimensional analogue of a torus? Could it have a topology where space loops back in hidden ways? Mathematically, yes. There are many possible ways to connect space. Some are simple, like a 3 torus, where each spatial dimension wraps around like our 2-dimensional square. Others are far more exotic, involving more complex manifolds and strange symmetries. But all of them raise a remarkable possibility. The universe could be finite and edgeless, not because it curves like a sphere, but because its connections fold space in on itself. And here's the wild part. We might be able to detect this. If space loops, then light could travel along multiple paths and arrive at the same place more than once. Imagine seeing a distant galaxy not once but many times from different angles. because its light has circled the universe in different directions. The sky could contain repeated patterns, like reflections in a funhouse mirror. These cosmic ghosts would be faint and hard to spot, but in principle, they could be there. Cosmologists have searched the cosmic microwave background for signs of this. The CMB is like wallpaper covering the entire sky, and if the universe has a non-trivial topology, it might leave behind repeating circles or matching patterns in that wallpaper. It's a bit like spotting the same flower print in different corners of your living room and realizing your wallpaper wraps around the house in a loop. So far, no definitive repetitions have been found. The universe looks smooth and largely uniform, without obvious signs of spatial looping. But the lack of evidence doesn't mean topology isn't interesting. It just means that if the universe is wrapped up in clever ways, it might be doing it on scales larger than what we can observe. Our observable universe has a limit. It only extends as far as light has had time to reach us since the Big Bang. Beyond that, there could be more space and more structure we simply can't see. And even within our observable patch, subtle topological effects could still be lurking. Some cosmologists have proposed models where the universe is shaped like a Poincaré dodecahedral space, a kind of 12-faced object where opposite faces are connected with a twist. Others explore shapes involving mirror symmetries, twisting identifications, and higher dimensional folds. These aren't just mathematical curiosities, they're attempts to make sense of the clues we see in the CMB and the structure of the cosmos. Topology also has implications for the universe's origin and fate. If space is finite, then the total amount of matter and energy might also be finite. That changes how we think about cosmic entropy, about what happens in the far future, and even about how time itself behaves. Some topological models could help explain certain anomalies in cosmic data. Others suggest that during inflation, that brief, blisteringly fast expansion of space in the early universe, topology may have been locked in, like a scar from the universe's birth pangs. And there's a playful side to all this too. What would it feel like to live in a multiply-connected universe? You might look out with a powerful enough telescope and see the back of your own head, not because of a mirror, but because light from Earth circled the cosmos and returned after billions of years. That's not just science fiction. It's a genuine, if highly speculative, consequence of certain topologies. Of course, these ideas are still theoretical. No one has sent a spaceship far enough to test the looping nature of space firsthand. And light, while fast, takes a long time to circle a universe that could be billions of light years across. So we rely on indirect tests, looking for patterns, matching structures, and subtle echoes in the cosmic light. It's a bit like trying to figure out the shape of a room you're locked inside by studying the echoes of your own footsteps. But even without definitive answers, topology gives us a richer language for thinking about space. It reminds us that shape is more than curvature. It's about structure, connection, and continuity. You can have a flat universe that loops, a curved universe that doesn't, or something in between, connected in ways we can barely begin to picture. And maybe that's the most beautiful thing about topology. It teaches us humility. Space isn't just a blank canvas for stars to glitter on. It might be stitched together, twisted, folded, or looped in ways that defy our everyday intuition. The universe doesn't need edges to be finite. It doesn't need infinity to be endless. It just needs connection. Somewhere out there, light may be tracing paths we can't yet see. The universe may be repeating itself in quiet patterns, echoing across space. And while we may not yet know exactly how space is stitched, we're learning to read the seams, one twist, one loop, one triangle at a time. Imagine playing an old arcade game, something pixelated and simple like Pac-Man. You move to the edge of the screen and suddenly reappear on the other side. There's no wall, no transition, just a loop, smooth and seamless. You can chase ghosts in circles forever without ever hitting a boundary. That, in a surprisingly real sense, is one of the ways physicists think the universe might be shaped. Not as a grid of pixels or a screen, of course, but as a vast and subtle space where the edges are not edges at all, but connections. In the world of cosmic topology, we're allowed to dream a little weirdly. The universe might be infinite, or it might just feel infinite because it's looped back on itself in every direction. And some of the best metaphors we have for exploring this come from delicious, dizzying, and sometimes dizzyingly delicious shapes, like donuts, Mobius strips, and yes, even video game maps. Let's begin with a classic, the torus. This is the mathematical term for a donut shape, a ring where space loops around both horizontally and vertically. If our three-dimensional universe had the topology of a three-torus, it would mean that space is finite in size but has no boundaries. Every direction you move in would eventually bring you back to where you started, as long as you travelled far enough in a straight line. This is more than just a geometric curiosity. A toroidal universe is flat, meaning that on small scales it obeys Euclidean geometry. Triangles behave, parallel lines never meet, and the angles add up the way they should. But it's multiply connected, meaning you can cross it and end up on the other side, which is also the side you started from. If you've ever played a looping video game map or looked into a mirror maze, you've had a little taste of this logic. It's space on a clever loop, not curved like a balloon, but wrapped like a racetrack with no finish line. And it's not just the torus. There are many other exotic shapes that mathematicians have dreamed up to describe possible topologies of the universe. One of the most iconic is the Mobius strip, a two-dimensional surface with only one side. If you take a strip of paper, twist one end and tape it together, you get a surface that seems to flip your direction as you go. A tiny bug crawling along the strip would find itself walking on the other side without ever crossing an edge. It would return to its starting point, but reversed. Now, generalizing the Mobius strip into 3 dimensions becomes trickier, but it introduces the idea of orientation reversal, a strange topological property where space might not only loop, but subtly flip along the way. Imagine sending a spaceship on a long journey through such a universe and having it return, unchanged in location but mirrored in some internal way. That's the sort of strange possibility topology allows. Then there are Klein bottles, which are like Mobius strips taken up a dimension with a twist of their own, literally. They can't be properly embedded in 3-dimensional space without intersecting themselves, but in 4 dimensions they make more sense. Think of it as a bottle that loops through itself, where inside and outside are the same thing. You can't fill it with water, because any water you pour in never actually stays inside. It's all one continuous surface. The idea is more poetic than practical, but it opens up fascinating possibilities about how space could be knitted together. Even more whimsical are the ways we might visualize these ideas through games. The Pac-Man map is an example of a quotient space, where opposite edges are identified, mathematically glued together so that the player or traveller exits one side and enters the other. In 3 dimensions, imagine leaving one side of the universe in your spaceship and reappearing on the opposite side, perfectly aligned. It's not just a video game mechanic, it's a candidate model for our universe's topology. These wraparound models offer an intriguing answer to one of the oldest questions in cosmology. Does the universe have an edge? If space is infinite, then no edge is needed. But if space is finite, like a torus, it still has no edge. There's no wall you crash into. Instead, every path brings you back to where you began, without crossing a boundary. A bit like walking east on Earth, and eventually arriving back at your starting point. Except, instead of walking over a curved surface, you're moving through a flat but looping volume. Now, detecting these cosmic loops is no small task. Astronomers look for repeating patterns in the cosmic microwave background, similar structures in opposite parts of the sky that could indicate the universe wraps around. They also consider light paths. If the universe loops, then light from a distant galaxy might travel more than one route to reach us. We might see duplicate images of the same object, appearing in different parts of the sky, like mirrored echoes of ancient galaxies. So far, no firm evidence for such duplication has emerged. But that doesn't mean the universe isn't multiply connected. It could simply be that the loops are bigger than the observable universe. If the size of the wraparound exceeds what we can currently see, about 93 billion light-years across, then we wouldn't have any repeated light paths within our view. We'd be like fish in a small pond, unaware that the water curves in ways we can't detect from within. There's also something quite beautiful in these looping ideas. They offer a sense of continuity, of endlessness without infinity. A universe that folds in on itself is poetic in its economy. Nothing wasted, no edges, no boundaries, just one continuous flow of space, gently bending in unexpected ways. In philosophical terms, topology hints at a universe that is less like a sandbox and more like a tapestry, woven, closed, and quietly clever. It's not just about what's in the universe, but how the fabric itself is stitched. The shape of the cosmos becomes part of its story, part of what allows stars to form, galaxies to arrange, and light to journey across epochs. And in a strange twist, quite literally, some of these shapes allow for things like closed time-like curves, where paths through space-time might theoretically allow for a return to one's past. Time loops, memory loops, topological time travel. These are speculative ideas, of course, and often tangled with paradoxes, but they grow from the same mathematical soil that brings us our donuts and Mobius strips. What's perhaps most comforting, though, is the simplicity underneath it all. Whether it's a coffee cup and a donut sharing a topological identity, or a spaceship looping through an invisible torus, the universe seems to favour structure. Not chaos, not clutter, but elegant, rule-bound connections. Even the strangest shapes obey consistent logic. Even the most twisted paths follow gentle curves. So tonight, as you settle into bed, let your thoughts spiral gently through a donut-shaped universe. Drift with the idea that space might have no end, not because it goes on forever, but because it folds in just right. Imagine your dreams quietly walking off one edge of sleep and reappearing on the other, looping softly, peacefully, across the quiet structure of reality. Let's begin with a question that seems innocent enough. What's at the edge of the universe? It's the sort of thing kids ask during car rides or over a bowl of cereal. It feels natural, like asking what's beyond the mountains or what lies behind a closed door. But when it comes to the universe, that question quietly reshapes itself into a paradox. It's a bit like asking what's north of the North Pole. You can try to point there, but any direction you choose is still south. There isn't a location north of north, because the North Pole isn't sitting on a platform with more land behind it. It's not the edge of something, it's a limit built into the very structure of how we define direction. The same strange idea applies to space itself. When we ask about the edge of the universe, we might be asking the wrong kind of question. In everyday life, we're surrounded by things with borders. Books have covers, tables have edges, even oceans, vast as they are, end in shorelines. It makes sense to think that space, the biggest thing we know, should also have some kind of border. But here's where geometry and topology begin to gently untangle our assumptions. In cosmology, an edge isn't the same as a limit to distance. Space can be finite but edgeless, meaning you could travel forever and never hit a wall, not because the universe is infinite, but because it curves back on itself in a higher dimensional way. It's not unlike walking on the surface of the Earth. Keep moving forward and you'll never fall off the planet. Instead, you eventually return to where you started, even though you never change direction. Earth's surface is finite, but it has no edge. It's closed, but unbounded. Apply that same logic to three-dimensional space, and you start to get the idea of a closed universe, a cosmos that is finite in volume, but without borders or walls. If space curves in on itself in just the right way, then there's no place where space ends. There's simply more space looping around quietly, invisibly. This is a deeply comforting idea in many ways. If the universe has no edges, then there's no outside to fall into. No cosmic cliff waiting at the end of the road. Just a continuous expanse, joined up in all directions. Even if it's finite in volume, the experience of moving through it would feel endless. You might wonder, Could the universe still have a centre if it has no edge? And here again, our intuitions from smaller spaces mislead us. In cosmology, the universe doesn't have a centre, not in the way we imagine. The Big Bang didn't happen at a point in space. It happened everywhere, all at once. Space itself expanded and continues to expand, not from a central location but uniformly, with no preferred direction. Any observer, in any galaxy, sees themselves as stationary while the universe expands around them. It's not that we're at the centre, it's that every point in space behaves as if it were. This idea can be challenging because it violates how we think about objects and movement. If something is growing, shouldn't it be growing into something else? If space is expanding, what is it expanding into? But in general relativity, space doesn't need a surrounding space to expand into. It's not like a balloon inflating into the air. It's more like the surface of the balloon itself expanding. Only the surface, the two-dimensional skin, is what matters. For our universe, it's the three-dimensional fabric of space that's stretching. And just like the balloon surface doesn't need a bigger surface around it, our universe doesn't need an external space to grow into. Let's pause and consider a simple analogy. Imagine a video game character on a flat screen. That character experiences their world in two dimensions, left and right, up and down. They don't know about the thickness of the screen or the circuitry beneath it. For them, their world is complete and boundless in its own way. We, as the player, can see the screen's edges and corners, but to the character there's no outside. Now imagine that we are that character, and the third dimension we see is like the two-dimensional screen to them. If the universe wraps in higher dimensional ways, we wouldn't be able to step outside and look at it from the outside. All we have is what's within. In this model, asking about the edge of the universe is like the video game character asking what's off screen. They might imagine endless possibilities, but they'll never see it. For us, space just is, without needing a boundary to define it. This idea is more than philosophy. It's grounded in real models of space-time. The Friedman-Lemaitre-Robertson-Walker metric used in modern cosmology allows for universes that are finite and edgeless. It's part of the mathematical scaffolding that describes how the universe evolves over time, including expansion, curvature, and topology. These models don't require edges. They allow space to be shaped like a hypersphere or a torus, or more exotic forms that wrap and loop in ways that defy simple visualizations. Of course, we don't know the true global structure of the universe. Our instruments and telescopes can only see a limited patch, the observable universe. Beyond that, it's unknown whether space keeps going, loops back, or shifts in topology. But within the observable realm, we see no signs of an edge. Galaxies fill the sky in all directions. Light comes from every part of the sky, and it's all part of a consistent, continuous whole. One might also ask, what would it even mean to reach an edge? What would it look like? Would there be a wall? A sign saying, "Thank you for visiting the universe"? Physics doesn't provide a mechanism for such a barrier. There's no physical theory that predicts a literal edge, where space ends and something else begins. It would raise unanswerable questions. What's beyond the edge? What are the laws there? How would causality behave? Instead, the more elegant answer is, there is no edge. Not because the universe goes on forever necessarily, but because it doesn't require one. Space can be closed like a sphere, or twisted like a torus, or folded like a multidimensional quilt. But in every case, the math works best when space is continuous, self-contained, and, just like the surface of the Earth, without ends. This doesn't mean we're trapped. It means we live in a universe that might be complete, whole, and quietly self-referential. One where the horizon is not a limit but an invitation. A reminder that even if we could fly our telescopes past every galaxy, we might still be looping back home, unknowingly. So the next time someone asks what's at the edge of the universe, smile and ask them what's north of the North Pole. Then watch their mind gently crinkle in curiosity, the way space itself might fold in on its own mysteries. Picture yourself standing in a wide open field on a moonless night. No buildings, No lights, just sky. As you look up, you're seeing light that has travelled across vast distances of space to reach you. Some of it began its journey when you were brushing your teeth earlier that day. Some of it left its source when dinosaurs were still roaming. And some of it started travelling across the cosmos billions of years ago, before Earth even existed. And yet, as far as you can see in any direction, that view has a boundary. Not because the universe ends there, but because light hasn't had enough time to reach you from farther out. This forms what we call the observable universe, a spherical bubble around you, filled with everything light has managed to deliver since the universe began. It's not a limit of what exists, just a limit of what we can currently observe. The observable universe extends roughly 46 billion light years in every direction from where you sit. That's a staggering span, a distance so large it barely feels real, but it's only a tiny portion of the actual universe, which may be vastly larger, or even infinite. We just can't see the rest because the light from those faraway regions hasn't had enough time to get here. The universe is about 13.8 billion years old, but thanks to the expansion of space, the edge of the observable universe lies much farther out than 13.8 billion light years. Space has been stretching the entire time, pulling galaxies apart even as their light rushes toward us. And just to make things a little trickier, your observable universe isn't the same as your neighbours, or a giraffe's, or a galaxy's. Every observer, no matter where they are in space, has their own bubble of visibility centred on themselves. It's like everyone is at the centre of their own cosmic snow globe, watching flakes that drift in from different distances and times. And yet all of these globes overlap and blend into one another, creating a shared, though incomplete, view of reality. The term observable might sound limiting, but it's actually quite rich. Within that 46 billion light-year radius, we can detect galaxies, quasars, pulsars, supernovae, and even the faint hiss of the cosmic microwave background, the leftover glow from the Big Bang. These photons have been travelling for nearly the entire age of the universe, gently stretched into microwaves by cosmic expansion. They provide a kind of baby picture of the universe, a snapshot of what it looked like just 380,000 years after it began. But what lies beyond that visible shell? What's out there in the actual universe, beyond our observational reach? The honest answer is we don't know, but there are strong clues. Because the observable universe looks roughly the same in every direction, what scientists call isotropic, and because the laws of physics appear to work the same everywhere we look, it's reasonable to think the universe continues beyond what we can see. This assumption is known as the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales, and that our location in space isn't special. We're not at the centre, we're just in a typical spot. That means the actual universe is almost certainly much larger than what's visible, possibly trillions of light years across, possibly infinite, and it may be far stranger than we imagine. Some models suggest the universe could be shaped like a three-dimensional torus, finite but looping in all directions. Others suggest vast open expanses that stretch forever. In either case, the regions we can't see might host completely different arrangements of galaxies, different patterns of matter, and even regions where physics itself behaves a little differently. Not in a fantasy way, but in subtle shifts. Maybe different ratios of dark matter to baryonic matter, or slight variations in density that form different kinds of structures. Even more intriguingly, if cosmic inflation occurred in the early universe, as most cosmologists believe, then space didn't just expand. It exploded outward at faster than light speeds, smoothing and flattening everything in the process. But inflation didn't necessarily stop everywhere at once. In some theories it continued in other pockets of the universe, spawning new regions with their own big bangs, their own physics, and their own bubbles of expansion. This is the concept of the multiverse, though it's important to distinguish that from science fiction's idea of parallel dimensions. Here, it refers to regions of space-time so far removed from us that we could never interact with them. even if we waited an infinite amount of time. Back in our own cosmic bubble, the observable universe gives us an exquisite laboratory. We can map the large-scale structure of galaxies, trace dark matter through gravitational lensing, and even infer the shape of space through measurements of ancient light. But we do all this while knowing that what we see is only part of the whole, possibly a very small part. And that leads to one of the most mind-bending realizations in modern cosmology. We cannot ever see the entire universe, not just because our technology is limited, but because light itself moves at a finite speed and space keeps expanding. There are galaxies out there that we can see now, but whose light was emitted billions of years ago. Since then, they've moved so far away, dragged along by the stretching fabric of space, that their light will never reach us again. They are slipping beyond our cosmic horizon, fading into invisibility. It's not that they're blinking out of existence, it's that the road between us and them is stretching faster than light can cross it. This boundary is called the cosmic event horizon, and it's a deeply poetic concept. There are things out there we can see today, but can never visit, places whose future we will never know, and perhaps most humbling of all, there are parts of the universe that will never know we existed. Still, the observable universe is enough to fill a lifetime, or many lifetimes, of curiosity. It contains over 2 trillion galaxies, each with hundreds of billions of stars. That's more stars than grains of sand on Earth. More planets than we could ever dream of naming. It's not a small stage. It's a vast dynamic theatre, constantly unfolding in new ways, even as we can only glimpse the actors on its closest edge. So tonight, when you look up at the stars, or just imagine them from beneath your cosy blanket, remember that you are peering out from the inside of a sphere of light. 13.8 billion years of cosmic history washing gently into your eyes. You're at the centre of your own observable universe, not by ego or design, but by the quiet laws of physics. And beyond that glowing shell, a great mystery. A silence filled with possibility. The rest of the universe might be very much like ours, or not at all. It might go on forever, or loop back on itself. It might even be one of many. But for now, we rest inside our luminous bubble, listening to the echoes of ancient light and wondering what lies beyond the veil of the visible. Welcome to the strangest safari you'll ever take, one without lions or zebras, but filled with peculiar creatures like Klein bottles, projective planes, and something called a 3-manifold. These aren't animals that walk or crawl, but mathematical beings, the kind that live quietly in the minds of geometers and cosmologists. They don't eat, sleep or roar, but they do bend and twist and loop through dimensions in ways that seem almost alive. Let's begin with the gentle giant in this zoo of shapes, the Klein bottle. If you've ever made a Mobius strip, a simple twist of a paper loop where one side becomes 2, you've dipped a toe into the world of non-orientable surfaces. A Klein bottle is the next step up. Imagine taking a tube, bending it around and connecting one end to the other, but with a twist, so that the inside becomes the outside without ever passing through a boundary. Sounds reasonable, right? The catch is, you can't do this in 3-dimensional space without the tube passing through itself. In 4 dimensions, however, the Klein bottle makes perfect sense. What makes the Klein bottle so delightful is its refusal to play by our intuitive rules. It has only one surface, no inside, no outside. Pour water into it and, mathematically speaking, there's no in to fill. It defies the tidy logic of teapots and soda bottles. And yet its topology is entirely consistent, even elegant. You can draw mathematical maps across its surface, study how loops stretch and shrink, and explore how its structure connects with other exotic spaces. Moving through the zoo, we encounter a whole family of strange shapes called manifolds. In the simplest terms, a manifold is a space that, on a small scale, looks like ordinary flat space, but globally may be curled, twisted, or otherwise bizarre. A line is a one-dimensional manifold. A sphere is a two-dimensional manifold wrapped into 3 dimensions. But in cosmology and abstract mathematics, we're most interested in 3 manifolds, spaces where every tiny region feels like normal 3-dimensional space, but the overall shape might be anything from a torus to a multi-looped monstrosity. Some 3 manifolds are compact and finite like a torus, while others are infinite and open. Some are orientable, meaning you can consistently define left and right throughout the space. Others are non-orientable, meaning your sense of direction might flip if you take a long enough walk. Imagine setting off on a spacewalk only to return with your left glove on your right hand, without having turned around. That's not just weird, that's topology. And then there's the wildest part. Some of these spaces can't be embedded in our 3-dimensional world at all. You can't build them with clay or cardboard, or even with the most sophisticated 3D printer. They exist purely in mathematical reality, visualized with equations, simulated with supercomputers, and explored through logic rather than sight. Yet despite being abstract, they could describe the true shape of the cosmos. One famous example is the Poincaré dodecahedral space. It's built by taking a dodecahedron, a 12-sided shape made of pentagons, and identifying opposite faces but with a twist. Every time you pass through one face, you re-enter from the opposite side, rotated by 1/10 of a full turn. If this were the shape of the universe, travelling in a straight line would eventually bring you back to where you started, but not facing the same way. You'd loop and twist and turn, all while moving in what feels like a straight line. The space is finite but without edges, perfect for a cozy looping cosmos. Scientists have even searched for signs of this topology in the cosmic microwave background, looking for matching circles on opposite sides of the sky, echoes of light that might have wrapped around the universe and met itself again. So far the results have been inconclusive, but the search continues. After all, if our universe is a dodecahedral loop, it would be quite the architectural surprise. Then there are Seifert fibred spaces which sound like something you'd use to knit an interdimensional scarf. These are 3 manifolds where the space can be broken down into loops, circles woven together in structured ways. Mathematicians categorize them with ornate diagrams and long lists of symbols, but you can imagine them as cosmic yarn, looping and layering to form a universe with internal symmetry. If string theory turns out to have any bearing on reality, these spaces might become more than just mathematical curiosities. We also have projective planes, another non-orientable surface where each point is connected not just by straight lines, but by directionless loops. These arise when you take a regular plane and glue together every pair of opposite points, east with west, north with south. The result is a surface where turning around isn't optional, it's required. You cannot maintain a fixed orientation in such a place. Directions like socks in the laundry simply vanish or get mysteriously reversed. All of this, Klein bottles, Mobius loops, dodecahedral twisty spheres, brings us to a strange realization. The universe doesn't have to be built out of the simple building blocks we know from everyday life. Just because we grew up with boxes and balls and triangles doesn't mean the cosmos obeys those forms. It might be curled in dimensions we don't directly perceive, wrapped in higher dimensional symmetries, or stitched together in topologies that only make sense in the realm of math. And yet these shapes aren't just idle fantasies, they're part of the toolset cosmologists use to understand what's possible. If the universe is finite, it needs a topology. If it has no edges, it needs a structure that loops. And if it started in a quantum froth of energy and inflation, it may have settled into one of these mathematical habitats, silent, symmetric, and strange. Even the language of topology has its own sleepy rhythm: homotopy, isometry, Euler characteristic, genus, words that hum gently in your ears, even if you don't know exactly what they mean. They mark the ways we try to classify the untouchable, how one space can be bent into another without tearing, how loops behave in different geometries, how we count the invisible features of a space that never ends. And that's the joy of the topological zoo. It's not about finding animals to cage or paths to follow, It's about possibility, a celebration of form without fixedness, of loops without ends, of shapes so delicately strange that they feel like dreams spun in equations. As you drift off tonight, imagine walking through a Klein bottle. Your footsteps echo softly on a floor that loops around into itself. Walls gently flip and fold, never quite ending, never quite beginning. No doors, no windows, just the quiet sensation of space curving not around you but through you. The universe, perhaps, humming to itself in the shape of something beautifully unknowable. If you were to ask a child where the centre of the universe is, you might get a confident answer. Right here, usually accompanied by a grin and a stomp of the foot. And in a way, they're not entirely wrong. Because in the strange, elastic, expanding space we call the cosmos, every point behaves a bit like a centre, including the patch of space right underneath your pillow. But that doesn't mean the universe is a giant celestial dartboard with Earth bullseyed at the middle. Quite the opposite. The idea of a central point in the universe is one of those concepts that feels natural in our everyday world, but starts to unravel the moment we try to scale it up to cosmic proportions. Let's start with something more familiar. A balloon. Not the kind that floats at birthday parties, but a plain old air-filled balloon with dots drawn all over its surface. As you blow it up, the balloon expands and the dots move away from each other. No single dot is the special one from which all others are fleeing. From the perspective of any given dot, it seems like everything else is retreating. That's how cosmic expansion works. Space itself stretches, and galaxies carried along with it all appear to recede from one another. The important part of this analogy isn't what's inside the balloon, but its surface. Imagine a two-dimensional creature, let's call her Dotty, living on that surface. Dotty can move left, right, forward, and backward, but she has no concept of up or down. Her universe is the curved skin of the balloon, and as it expands, she sees more space open up around her. From her view, everything's moving away, and she might be tempted to believe she's at the centre of it all, but there is no centre on the surface. The centre exists only in a third dimension she can't access. Now take that concept and bump it up one more dimension. Our universe isn't expanding into anything. It's not a balloon floating in a higher space. The space itself is growing. The distances between galaxies are increasing, not because they're flying through space, but because space itself is stretching. And just like Dotty, we see everything moving away from us. Every distant galaxy seems to recede. But that doesn't mean we're special. It just means that expansion looks the same from every vantage point. This is the beauty of homogeneity and isotropy. Two gentle, elegant principles that say the universe is roughly the same in every location and in every direction on the larger scales. These ideas are woven into the fabric of modern cosmology and baked into the equations that describe our universe's behaviour. There are no cosmic VIP seats, no central throne, just lots of galaxies gently drifting apart at every corner of the cosmos. Of course, back in the old days, say a few centuries ago, it was assumed that Earth was the centre. It made sense at the time. After all, the sun rose and set, the stars spun overhead, and nothing felt particularly like it was moving unless you squinted very hard. But Copernicus nudged Earth out of the spotlight, and later thinkers like Galileo and Newton sealed the deal. The universe, it turned out, didn't revolve around us, and with the dawn of modern astronomy, we learned that even our galaxy is just one of billions, or more. Still, we're stubborn creatures. The idea of a centre is comforting. It gives us orientation, grounding, a place to pin our maps. So what does it mean to ask where the universe's centre is? Well, here's the surprise. In a way, you are the centre, but so is everyone else. Because of the way light works and the way space expands, every observer in the universe sees themselves as sitting in the middle of their observable sphere. You look out and see galaxies receding in all directions. So does someone in a galaxy 10 billion light-years away. Every point in the universe has the same view, just with different arrangements of nearby stuff. It's like being in the middle of a vast fog. Wherever you stand, you're in the centre of the clearing you can see. And yet, despite this universal equality, the universe isn't completely featureless. It has structure, webs of galaxies, clusters, voids, and those structures do have centres of gravity. Our own Milky Way galaxy has a central bulge of stars, and deep within that, a supermassive black hole anchoring its swirl. Our solar system has the sun at its heart. Earth has a core of molten metal, so locally centres are real and important. But scale out far enough, and the idea of a single universal centre dissolves into the background hum of expansion. There is, however, one kind of centre that does have a meaningful definition in cosmology: the centre of the Big Bang. But here's the twist. The Big Bang didn't happen at a point in space. It happened everywhere. It was the moment when all of space was infinitely dense, infinitely hot, and began to expand. Not from a single location, but uniformly across all of space. Every point in our universe was once squeezed together with every other point. There was no outside, no place you could stand and watch it happen from a distance. In that sense, the centre of the Big Bang is everywhere, which means the centre of the universe is also everywhere, including your living room. Now, if you're picturing that with a slight squint and a furrowed brow, you're not alone. It's one of those ideas that resist clean visualization. Our brains evolved to navigate forests and cliffs and dinner tables, not to conceptualize a four-dimensional, edgeless, expanding geometry. It's perfectly okay to find it weird. Most physicists do too. There are also alternative models and thought experiments that explore different kinds of centrality. Some versions of the multiverse, for example, have individual bubble universes that expand like little firecrackers in a cosmic foam. In those models, each bubble might have its own centre of expansion. But again, it's not a centre in the classic sense. It's more like a focal point of symmetry, not a throne atop which a cosmic ruler might sit. And if the universe is infinite, and it might be, then asking for a centre becomes like asking for the middle of an endless number line. You can pick any point and declare it the centre, but that's just a choice, not a fundamental truth. The infinite has no favoured position. It stretches on forever in all directions, politely refusing to offer a midpoint. So, does the universe have a centre? Not in the way we usually mean. But that doesn't mean you aren't central in a more poetic sense. You are the centre of your observable universe. You are at the heart of your own cosmic horizon. Everything you see, from nearby stars to ancient light, is centred on your location. Not because the cosmos is making you special, but because that's how time and space work together to deliver light to your eyes. It's a humbling idea, and also a strangely comforting one. In a universe without edges or anchors, we each get to be the centre of our own little sphere, watching galaxies glide by and wondering where, if anywhere, it all begins. So lie back and let that thought settle in. You're not the centre of the universe, but the universe is centred around you. And that, in its own quiet way, is a beautiful kind of symmetry. Take a moment to picture the edge of the universe. Maybe you imagine a towering wall of darkness, or a glowing curtain fluttering in the cosmic breeze, separating everything we know from an absolute nothingness beyond. Maybe you imagine stars clinging to the last visible pixel of reality, teetering over some unimaginable brink. It's a compelling idea. Our everyday experience teaches us that things have boundaries. Every room has walls, every book has covers, every slice of cake, sadly, has an end. But when it comes to the universe, that instinct can lead us astray. The notion of a cosmic edge is one of those charming illusions, like the horizon at sea. It looks like the ocean stops in the distance, as though the water runs out. But when you sail toward it, it simply moves with you. It's not a real boundary, it's a perspective effect, born of curvature and distance. The edge of the universe, if it exists at all, might be something like that. Not a wall, not a line, but a feature of how we see and interpret space. In fact, current cosmological models suggest that the universe has no edge at all, not because it goes on forever in a straight line, but because of how space itself is shaped. It might be infinite, stretching outward in all directions with no end, or it might be finite, but unbounded, like the surface of a sphere, a shape where you can keep travelling without ever hitting a wall, eventually looping back to where you started, just in 3 dimensions instead of 2. To make sense of that, let's shrink things down. Imagine an ant crawling along the surface of a balloon. It can walk endlessly without ever encountering a wall or falling off the edge. The balloon has a finite area, but no boundaries. There's no end to its world. Now imagine that same concept in 3 dimensions. Our universe could be curved in such a way that it wraps back around on itself, forming a closed, continuous space with no need for a literal edge. Of course, we humans love the idea of something outside. If the universe is a kind of container, what's outside the container? Is there more space, more time, a larger reality? But this assumes that the universe exists inside something, like raisins inside a loaf of bread. In truth, space itself is not an object floating in a larger space. Space is what everything else floats in. And if the universe is infinite, there is no outside. Infinity doesn't need an edge. It simply keeps going. Now it's possible that the universe is only locally flat and infinite looking, while actually being finite and multiply connected, looping around itself in ways that are difficult to visualize. In that case, the illusion of infinity would come from the repeating geometry of space. You could travel forever, but eventually pass the same stars over and over again, like a cosmic version of a looping video game map. Even stranger, the universe might have a complex topology, with higher dimensional twists and turns that make concepts like outside or edge meaningless. In such a case, the universe could be shaped like a 3-dimensional torus, or even more exotic spaces like a dodecahedral manifold. In these models, space connects back onto itself in multiple directions. You could travel in a straight line and end up right back where you started, without ever making a turn or hitting a wall. And if that makes your head tilt slightly, you're in good company. Our brains are wired to think in straight lines and boxes. We grew up in rooms, not in spaces that loop back on themselves. But the universe doesn't owe us intuitiveness. It just keeps humming along in whatever shape it pleases. From an observational standpoint, we've looked for signs of an edge, or anything that might resemble one. One idea is that if the universe were finite and wrapped, we might see repeating patterns in the cosmic microwave background, like the same galaxies or features showing up in opposite directions of the sky. So far, we haven't found compelling evidence of that, but our instruments and methods have limits, and space might be just subtle enough to hide its true nature beyond the reach of our current tools. Another intuitive trap is to think of the Big Bang as an explosion in space, with matter flying outward into some kind of cosmic emptiness. But the Big Bang didn't happen in one spot, and it didn't explode into anything. It was the rapid expansion of space itself, happening everywhere at once. There is no central point it sprang from, and no edge it's expanding toward. The universe isn't growing into something. The fabric of space is simply stretching, carrying galaxies with it. This can lead to a very quiet kind of vertigo. If the universe doesn't end and doesn't have walls, then where are we? What's holding it all together? The answer is, in a sense, nothing is holding it together. It's just the shape that space happens to take. Gravity, dark energy, the initial conditions of the Big Bang, and the geometry of space-time itself all combine to produce the large-scale structure we see. And within that structure, there are no cosmic fences, no signposts saying, "You are now leaving the known universe." In a way, the absence of edges is freeing. It means there's no boundary where exploration must stop, no final curtain, just the continuing mystery of what lies farther and what lies deeper. And for those who like a poetic thought before bed, you are floating in something that, as far as we can tell, never ends. And even if it does, we may never reach it or even recognize it as such. Now, could the universe have a true edge, some abrupt boundary beyond which there is no space, no time, no physics? It's theoretically possible, though deeply problematic. A physical edge would raise all kinds of thorny questions. What happens at the boundary? What laws apply there? And how would such a thing come to be? Most theories avoid this altogether by simply eliminating the need for an edge in the first place. No boundary means no boundary conditions, just continuous smooth space. And even if some exotic version of an edge existed, it's quite likely that light from that region could never reach us. It would be outside our cosmic event horizon, forever hidden from view, like a distant ship sailing behind the curve of the Earth. We could know of its possibility but never confirm it. A perfect recipe for scientific humility. So the next time you hear someone ask, "What's at the edge of the universe?" you can smile gently and say, "That's like asking what's north of the North Pole." It's not that the question is silly, it's just that it assumes a structure that doesn't seem to exist. Edges are for pages and pizza slices and puzzle pieces. The universe, it seems, prefers curves, loops, and infinities. It prefers to stretch and fold in quiet, subtle ways, defying our need for corners and containers. And maybe that's just as well. After all, some of the best dreams take place in rooms with no walls, just open sky, endless horizon, and the slow drift of galaxies gliding away into the soft, edgeless dark. When you think about time, chances are you picture it as a line, one long straight arrow pointing from the past toward the future. Birth to school, school to work, work to retirement, and then off you go into the grand unknown. It's tidy, it's linear, it makes sense. But nature rarely sticks to straight lines just to please our sense of order. In the deep architecture of the cosmos, time, like space, isn't fixed. It bends, it curves, and in some of the stranger corners of physics, it might even fold in on itself. Let's start with something Einstein would nod at in approval. Space-time. It's not just a poetic mashup of two separate things, it's a single four-dimensional fabric where space and time are inseparably linked. The moment Einstein dropped his theory of general relativity into the world, he revealed that gravity isn't a force pulling objects across a static background. Instead, it's a feature of space-time curvature. Massive objects like stars and planets warp this fabric, and that warping affects how both space and time behave, which brings us to a lovely but slightly unsettling thought. Time itself can speed up, slow down, and even stretch, depending on the presence of mass and energy. Clocks on mountaintops tick slightly faster than those at sea level. Satellites orbiting the Earth have to account for tiny shifts in time caused by the planet's gravity, and near something incredibly massive, like a black hole, time can slow to a crawl. This isn't just science fiction. It's been measured, verified, incorporated into the GPS systems we all rely on. Every time you get directions to the nearest bakery, there's a little piece of Einstein whispering through your phone, correcting for the curvature of time. But if gravity can bend time, could it also twist it, loop it? Could you fall into a nap and wake up before you ever closed your eyes? The idea that time might loop around itself is one of the strangest and most captivating in theoretical physics. These loops are called closed time-like curves, and they crop up in some very specific solutions to Einstein's equations. The equations themselves don't forbid them. The reality might be less cooperative. One famous example is the Gödel universe, a model proposed by mathematician Kurt Gödel in the 1940s. In this rotating universe, the very structure of space-time allows for paths through space and time that eventually lead back to their own beginnings. If you followed one of these loops, you could, at least mathematically, end up back where you started, not just in space, but in time. Imagine baking a cake, then walking in a big circle and arriving back in your kitchen just in time to see your earlier self putting the batter in the oven. Or sitting down to rest, only to find that your nap lasted not minutes but an entire temporal loop, waking up just before you lay down. This kind of thinking quickly tangles into paradox. The classic one, of course, is the grandfather paradox. If you go back in time and prevent your grandparents from meeting, do you cease to exist? And if so, how did you travel back in time to mess things up in the first place? To sidestep these kinds of mind knots, physicists have explored whether the laws of the universe quietly prohibit closed time-like curves. Stephen Hawking famously proposed the chronology protection conjecture, which basically sees the universe protects causality the way a museum guard protects the Mona Lisa, firmly and with a healthy dose of side-eye. The conjecture suggests that any attempt to create a time loop would be undone by quantum effects or physical instability. Time, in other words, would protect itself from being broken. Still, there's nothing in the raw math that says time must behave like a one-way street. In fact, time might have a shape that's far more complex, perhaps even toroidal, like a donut. In such a model, you could imagine time curving around in ways that allow for periodicity, cycles, and loops, without necessarily causing paradoxes. Some cosmologists have even speculated that the universe itself might be cyclic, not just in space, but in time, expanding, contracting, then bouncing back in a kind of eternal rhythm. And just like space can be curved locally while still appearing flat from a distance, time could be locally distorted by things like mass and velocity, while still giving the illusion of uniform flow when viewed from a comfortable couch. It's all relative, literally. So what would it mean for you if time had shape? Well, for one, it would mean your experience of time isn't universal. A moment that feels long and drawn out for you might be a blink for someone falling into a black hole. Astronauts travelling near the speed of light would return to Earth having aged less than the people they left behind. And depending on how extreme the space-time geometry is, you could, in principle, revisit past locations in both space and time by navigating the right kind of curve. It also means the arrow of time, that steady march from past to future, isn't built into the laws of physics in a fundamental way. The equations work just as well forwards as backwards. Time's directionality seems to arise from entropy, the tendency of systems to move from order to disorder. It's entropy that gives time its flavour. But in a low-entropy universe, or in certain curved geometries, that direction might not be so clear. In dreams and stories, we often play with this idea. Time machines, infinite loops, days that repeat. But the more we learn, the more it seems that reality might be even stranger than fiction. If time can be bent and twisted, then the shape of a moment could depend on your location, your speed, or the depth of the gravitational well you're sitting in. Time becomes pliable, less like a ruler, more like a silk ribbon. Now, does that mean we're all secretly living inside a time torus, destined to repeat ourselves every few trillion years? Probably not. Most physical models that allow for closed time-like curves are deeply unstable, or require exotic matter that might not exist. And even if they could exist, we'd need unimaginable technology to navigate them. But the fact that such paths are even allowed in the structure of space-time says something profound. It means time is not just a passive backdrop, it's a participant, a character in the story of the universe, not just the paper the story's written on. And that means the shape of time might be as important and as mysterious as the shape of space. So, as you wind down for the evening, consider this gentle possibility. Perhaps time is not a ticking clock, but a winding path. Perhaps it coils softly through valleys of gravity, drapes over the hills of motion, and folds in secret loops we can't quite see. Maybe, just maybe, time isn't rushing forward at all, but quietly curving around you like a warm blanket, infinite and still. And if that doesn't lull you into a pleasant nap, consider the most relaxing shape of all, the circle. Eternal, symmetrical, and never-ending. A loop where nothing is lost, only returned. A shape, not of clocks but of dreams. Imagine lying in a quiet room, eyes closed, when suddenly someone tells you, by the way, Everything you see, touch and experience, your chair, your cat, the stars, even your thoughts, might actually be a projection. You might lift an eyebrow, or maybe both, depending on how relaxed you were a moment ago. But this isn't a twist from a sci-fi film, it's a real idea in theoretical physics, and it's called the holographic principle. Before panic sets in, don't worry, your cat is not going to flicker out like a faulty projector bulb. This isn't about illusions in the everyday sense, it's about how the deepest levels of reality might be structured. The holographic principle suggests that everything in our three-dimensional universe, including time, could be encoded on a two-dimensional boundary far, far away. It's like living inside a very sophisticated cosmic hologram, with the illusion of depth emerging from something flatter than expected. But let's ease into this gently, like sliding into a warm bath of metaphysical possibility. To start, consider a regular hologram, the kind you might see on a credit card or a shiny sticker. It's a flat surface, but when you tilt it, you see a three-dimensional image. The trick is that all the information needed to describe the full 3D object is actually stored on that 2D surface. A hologram is more than a picture. It's a data encoding technique, and it's surprisingly efficient. Now take that same idea and stretch it to the scale of the universe. The question physicists began to ask was, could the entire universe work the same way? Could the three dimensions we move through be the visible consequence of data encoded on some faraway cosmic boundary? To get to the heart of this strange proposal, we need to rewind to a time when theoretical physicists were grappling with a particularly thorny problem: black holes. Black holes, those mysterious regions of space-time where gravity is so intense that not even light can escape, posed a problem for physics. According to classical ideas, once something falls into a black hole, it's gone forever. But quantum mechanics insists that information, any information, can't simply vanish. Ever. It's a universal rule. So, what happens to the information about the stuff that falls in? In the 1970s, Stephen Hawking discovered that black holes aren't completely black. They emit a faint glow, now called Hawking radiation, and over time they can evaporate away. But if that's true, and they eventually vanish, then what happens to the information they swallowed? Is it destroyed, or does it somehow survive? Enter physicist Leonard Susskind and his colleagues. They propose that the information might actually be stored on the event horizon of the black hole, the two-dimensional surface that marks its boundary. And from this line of thinking grew a larger, wilder possibility. Maybe everything inside the black hole could be described by the information on that surface. That was the seed, and the holographic principle grew from it. This idea got a serious mathematical boost in the late 1990s thanks to the ADA-CFT correspondence, a landmark discovery by physicist Juan Maldacena. In this model, a type of universe called anti-de Sitter space, which has a certain kind of curved geometry, can be exactly described by a quantum field theory living on its lower dimensional boundary. In other words, what happens in the bulk of this universe has a perfect twin written on its edges. Think of it like a cosmic duet, with each note on the surface corresponding to a harmonic in the interior. Now, our universe is not anti-de Sitter space. It appears to be flat or slightly positively curved. But the AD-CFT correspondence gave physicists a powerful tool to explore the holographic principle in other contexts. It showed that a universe can, in principle, be fully described by information on its boundary, and that space, time, gravity, and even particles might be emergent features, not fundamental ingredients. In holographic models, gravity becomes a kind of side effect. It pops out of the underlying data, like warmth radiating from a campfire you can't see. The surface encodes the rules. The space inside follows them. This is not just metaphysical musing. Some physicists believe this approach might be key to reconciling the two big pillars of modern physics: general relativity, which describes gravity and space-time on large scales, and quantum mechanics, which rules the tiny, jittery world of particles. Holography offers a possible bridge between these realms. But what would it feel like to live in a holographic universe? Well, exactly like this. If the holographic principle is true, it doesn't mean we're being tricked. It doesn't mean your toast is secretly 2D. It means that the mathematics describing reality at the deepest level might live in a different number of dimensions than we experience. What we see, touch, and measure would still behave exactly the same way. It's like discovering that your favourite song is encoded as a spiral of grooves on a vinyl record. The music is real. The dance is real. It's just that the information started out in a flatter form. There's something quietly poetic about this too. It suggests that the universe is efficient, like an elegant equation scribbled on a chalkboard. That the vast cathedral of galaxies, dust and light might be the unfolding of patterns written on a distant wall we'll never see. That the cosmos could be a kind of projected story, real, coherent, and meaningful, but emerging from a place beyond direct perception. It's worth noting that the holographic principle is still a hypothesis, not a settled fact. It has strong theoretical support, especially in certain models of the universe, but we haven't yet proven it applies to our own. Still, experiments in particle physics and observations of black holes might offer clues in the future, and the idea continues to inspire physicists, mathematicians, and philosophers alike. So, is the universe a hologram? We don't know, but it might be, and if it is, it would be the most exquisite projection ever created. A masterpiece of encoded information. A cosmic play unfolding in full, three-dimensional splendour, cast from a whisper-thin screen at the edge of space. A universe that looks, feels, and lives in 3 dimensions, while hiding its blueprints in 2. Just like dreams that feel deep, even when they're made of shadows. And whether or not it turns out to be true, there's something comforting in the idea that reality has layers, some seen, some imagined, and some waiting quietly behind the veil, just out of reach. Imagine waking up in a room you've lived in all your life. You know it well. It has 3 walls, a floor, and a ceiling. You've counted them, measured them, dusted their corners. Everything that exists in your world fits neatly within those dimensions. And then one day, someone hands you a tiny key and says, "There's a hidden door you've never noticed. It's been curled into the wallpaper this whole time." That's sort of what string theory suggests about the universe. To begin, let's take a gentle stroll through dimensions. The spatial kind, not the ones where people wear monocles and speak only in riddles. We experience the world in 3 dimensions of space. Up, down, left, right, and forward, backward. Add time, and you've got the 4-dimensional stage that Einstein's space-time plays out on. But string theory, one of the most ambitious and mathematically rich frameworks in physics, proposes something altogether more curious, that there may be more than 3 spatial dimensions, possibly 10 or even 11 in some versions. These extra dimensions aren't stretched out like the ones we're used to. They're not hovering behind the couch or tucked behind Jupiter. They're compactified, rolled up into incredibly small, intricate shapes, too tiny to see or measure directly. Picture a garden hose. From far away, it looks like a one-dimensional line, but up close, you see it's a cylinder. There's an extra dimension curled around it. Now, imagine that on an unimaginably small scale all around you. The reason physicists turn to these hidden dimensions isn't because they're trying to make the universe sound fancy. It's because the math demands it. In string theory, the fundamental building blocks of reality aren't particles, but tiny vibrating strings, loops of energy that oscillate in different ways. Their patterns of vibration determine what kind of particle they appear to be: electrons, quarks, photons. But in order for these strings to behave consistently, they need more than just 3 dimensions to wiggle in. The equations work only if you allow extra dimensions for the strings to explore. The most popular approach is called superstring theory, which requires 10 dimensions, 9 of space and 1 of time. An even more encompassing idea, M theory, proposes 11 dimensions. In these models, the familiar universe is like a flat sheet, or brain, floating inside a higher dimensional space. All the particles and forces we know, except gravity, are confined to our three-dimensional brain. Gravity, however, might be free to wander into the extra dimensions, which could explain why it feels so weak compared to the other forces. Now, if these hidden dimensions exist, why don't we notice them? Why don't we accidentally step into them when reaching for a cookie? Because they are incredibly tiny, curled up at scales close to the Planck length, which is about 1/10 of a trillionth of a centimetre. That's a number so small it's more of a whisper than a measurement. At that scale, even our most powerful instruments can't detect direct evidence of extra dimensions. But they might leave subtle traces. For instance, in particle collisions at extremely high energies, like those produced in large particle accelerators, extra dimensions could affect the behaviour of gravity or create unexpected particles. So far, we haven't spotted anything conclusive. But physicists keep looking, like careful detectives scanning the wallpaper for signs of a secret passage. Another fascinating consequence of curled-up dimensions is the idea that the shape of those tiny spaces could influence the properties of our universe. These compact dimensions aren't just boring loops, they could be twisted and knotted in fantastically complex ways, like tiny origami folded into Calabi-Yau manifolds, a term that sounds like a forgotten pasta dish but actually refers to specific geometries that allow string theory to remain mathematically consistent. The particular structure of these manifolds could determine everything from the masses of particles to the types of forces that exist. In this view, the physics of our universe emerges from geometry. The way the dimensions curl shapes the rules we live by. That's a bit like discovering that your personality is determined not by genetics or upbringing, but by the arrangement of invisible accordion folds in your bedroom ceiling. It's unsettling, but also deeply elegant. Some physicists have even speculated that different regions of a much larger multiverse might have different shapes for their hidden dimensions, resulting in entirely different physical laws. In that case, the universe we live in would be just one possible configuration among countless others, each arising from a different compactified structure. A quiet chaos of realities, all shaped by geometry we can't quite see. Of course, all of this rests on theory, not direct observation. String theory is incredibly promising, but also incredibly difficult to test. It has provided dazzling insights into black holes, quantum gravity, and the unification of forces, but the experimental evidence remains elusive. And yet, there's something undeniably peaceful in the idea that the universe hides its complexity so politely. These extra dimensions don't scream for attention. They don't glow or buzz or pulse. They simply curl up in silence, woven into the very fabric of space, gently guiding the notes of existence like a violin string humming in the background. If they're real, these hidden dimensions mean the world is more than it appears. That space is not just a stage, but a folded, resonant instrument, quietly shaping the dance of particles and light. And maybe, in some poetic sense, that's true of us too. That what we see is only part of the whole. That we move through life within a tapestry richer than we know, stitched with hidden curves and silent harmonies. So as you drift off tonight, imagine the corners of space curled like petals, soft and folded, whispering the secrets of physics in a tongue too small to hear. A lullaby, tucked into the seams of reality itself. Imagine trying to measure the ocean with a teacup. You dip it in, pour it out, repeat the process 1,000,000 times, and still feel like you've barely made a dent. That's more or less the challenge cosmologists face when they try to study the universe. Except instead of water, they're working with space, infinite space, and instead of teacups, they have telescopes, equations, and most importantly, light. The universe, at least as far as we know, might be infinite, not just big, not just wow, that's a lot of galaxies big, but truly without bounds, no edge, no ending, just more space, continuing forever in every direction. It's a concept that doesn't sit easily in the human mind. We're used to rooms with walls, forest with borders, roads with destinations. Infinity doesn't behave. So how do we measure something that doesn't stop? We start with what we can see. And that gives us a useful and comforting limit. The observable universe. This is the bubble of space from which light has had enough time to reach us since the beginning of the universe, about 13.8 billion years ago. But because the universe has been expanding all that time, the radius of this observable region is much larger, about 93 billion light-years across. Inside that bubble, we can observe galaxies, cosmic microwave background radiation, and structures stitched together by gravity. But beyond that, it's not that space ends. It's just that light from those more distant places hasn't had time to reach us yet. The cosmic conversation is ongoing, but we haven't received all the messages. And here's where the fun begins. Physicists use something called a light cone to figure out what regions of space and time are causally connected. Imagine a flashlight turned on in complete darkness. Its beam widens the farther it travels, like a cone of influence expanding outward. That's your future light cone. Everything your light can eventually reach. Now reverse it. The past light cone represents everything that could have influenced you up to now. Everything you've seen, heard, or measured, everything inside your observable universe, falls within that past light cone. So when we talk about measuring the universe, we're really talking about measuring the light that falls within our cone. And thankfully, space is transparent enough to allow us some very distant peaks. Telescopes like Hubble and James Webb act as cosmic time machines, capturing photons that have travelled across billions of years. Some of those photons were set loose when the universe was just a few 100,000 years old, a mere baby by cosmic standards. But even with the sharpest eyes and most sensitive detectors, there are limits. There's a boundary to what we can ever know. Beyond that edge, space might go on forever, or it might loop back around in some topological trick. But unless light from those regions makes it into our cone, we are left to guess. This is where cosmic models come in. Astronomers take what we can observe, galaxy distribution, background radiation, redshifts, and use that data to build models of the universe's geometry and expansion. These models tell us how fast the universe is growing, what it's made of, and how it might evolve. But they also come with assumptions, like that the universe looks roughly the same in all directions and from all locations. This principle, called cosmological homogeneity and isotropy, is our best tool for turning a partial view into a broader understanding. Think of it like standing in a foggy meadow. You can't see past a certain distance, but you assume that the grass and trees continue beyond the mist, more or less in the same way. It might not be a perfect assumption, but it gives you a working map. Now what if we wanted to measure more? To go beyond the horizon of light? Well, we can't. Not directly. There are no particles, no messengers faster than light, no shortcuts through the fog. But that hasn't stopped scientists from getting creative. Some have proposed looking for gravitational waves from before the cosmic microwave background was released. These waves, which ripple through space-time itself, might carry information from even earlier epochs of the universe, if we can build sensitive enough detectors to hear them. Others look to the shape of space itself. If the universe is finite and loops back on itself, light might eventually return from the other side, like a message bouncing off a cosmic mirror. In theory, we could spot repeating patterns in the cosmic microwave background, like seeing the same constellation in two different directions. So far, we haven't found that evidence, but it remains an open question. And then there's the concept of cosmic inflation, the idea that in the first tiny sliver of a second after the Big Bang, the universe expanded faster than the speed of light, stretching tiny quantum fluctuations into the seeds of galaxies. This inflation explains the uniformity of the cosmos and why space appears flat on large scales. But it also suggests that most of the universe lies beyond our observational bubble, expanded so far away that we'll never interact with it. In that view, the observable universe is like a snow globe resting on a vast, endless table of other snow globes. Some may be similar, others wildly different, and we're forever sealed in our own, able to shake it, study it, admire it, but never peek inside the others. All of this leads to a strange but serene conclusion. We measure infinity not by grasping it, but by understanding its shape through slivers, like studying a mountain through its shadow, or mapping an iceberg from the tip that breaks the surface. In practice, we keep refining our instruments. New surveys scan millions of galaxies. Observatories chase distant supernovae, trying to pin down the rate of cosmic acceleration. Radio telescopes peer deep into the cosmic microwave background, teasing out subtle curves and clues. Every observation adds a brushstroke to the canvas. It may never be complete, but it becomes more beautiful with each pass, and perhaps that's the secret to measuring the infinite. You don't need to see the edge, you just need to see enough to understand the pattern, like listening to the first few bars of a symphony and knowing there's a whole orchestra behind it. So tonight, as you relax beneath your blanket or stare softly into the darkness, think of the universe as a vast ocean of space and time. You may never touch the farthest shore, but the waves that reach your shores, those ancient beams of starlight, those cosmic ripples, carry with them the whisper of forever. And with every gentle question we ask of the stars, we inch closer to knowing the unknowable, not with teacups, but with light. Not by conquering infinity, but by learning how to listen to it. Imagine lying still under the stars, eyes half closed, the hush of the night folding gently around you. The air cools, thoughts drift, and the sky above becomes not just a collection of lights, but a question without a question mark. You wonder, not about what's out there, but about what it all is. What shape does reality take when no one is looking? What form does the cosmos hold when the lights are off and only silence remains? We've spent lifetimes asking this. Cultures across millennia have wrapped poetry and mathematics around the same mystery. Where does the universe begin and end? And what does it look like beyond the veil of stars? For most of history, these were sacred musings. The dome of heaven, the wheel of time, the celestial river, the turtle that holds up the world. Each shape told a story. Each story reflected back the shape of the storyteller's mind. Now, with the tools of science, we've traded the myths for models. We build telescopes, simulate universes, sketch out equations so long they fold in on themselves like origami. And yet, beneath all that effort, a very human wonder persists. When we ask about the shape of the universe, we're also asking something more personal. Where are we in all this? And what does it mean to be here at all? The answer for now is curiously gentle. The universe might be flat like an endless tablecloth, or curved like a sphere without edges, or saddled like a cosmic canyon stretching into infinity. It may loop back on itself, ripple with hidden dimensions, or be a projection from some deeper layer of information. And though we cannot yet grasp its full form, we've learned this much. Space is not static. It stretches. It breathes. It responds. And it doesn't need boundaries to be whole. But maybe that's the part that stirs us most. The universe is vast, yes, but it is also shapely in the truest sense. Not in the way a sculpture is shaped by hands, but in the way a river finds form in its flow. Geometry becomes not just a description of space, but a story of how space behaves, how it stretches, folds, ripples, and carries light, and us. Even our thoughts trace shapes, loops of memory, spirals of curiosity, tangents of fear and wonder. To ask about the shape of the universe is, in some quiet way, to turn our minds inward too. Our dreams and perceptions are part of this cosmos. The brain, curled into folds like hidden dimensions, makes models of reality with whatever starlight it can gather. Some physicists and philosophers even wonder whether consciousness itself might be related to the shape of space and time. Perhaps the very act of observing the universe helps bring its structure into clarity. Perhaps minds are like localized eddies in a much larger stream, momentary centres of awareness within an unfolding shape we can't fully see. And yet, you don't need a telescope to feel connected to this geometry. You are made of atoms born in stars. Your bones remember gravity. Your breath echoes a rhythm set billions of years ago. You're not floating in space, you are space, arranged into a temporary pattern called a person. That might sound poetic, but it's also literal. The particles in your body are quantum fields stretched across the same reality that extends to the edge of the cosmic microwave background. Your thoughts happen in curved space-time. Your heartbeat is just the local ticking of time, which bends differently in every corner of the cosmos. You're not separate from the universe, you're a phrase in its ongoing sentence. And what of the shapes we've imagined but haven't yet proven? Torus and Mobius strips, Calabi-Yau manifolds, holographic screens and cosmic brains. They might remain mathematical dreams, or they might someday be revealed as the scaffolding of all we know. Either way, there's something beautiful in the search itself. Not because we expect a final answer, but because the act of asking, gently, patiently, persistently, lets us touch something deeper. There is a strange kind of stillness that comes from contemplating the shape of the universe. It's not a silence of absence, but a silence full of structure. A stillness like snow falling in a forest, quiet, but patterned. Unknown, but not unknowable. And in that stillness, a kind of peace. You don't have to figure it all out tonight. You don't need to map every manifold or plot every curve. It is enough to know that the question exists, and that you are part of the answer, however briefly, however softly. So maybe in the end, the shape of reality is not something we stand outside of and describe, but something we live inside, like a dream that feels vast and real, even as we drift towards sleep. The edges blur, the lines soften, and all that remains is the feeling that the universe is not a machine to be solved, but a melody to be listened to, slowly, quietly, with wonder. You're here. The universe is wide, and somewhere between the light years and the eyelids, the shape of dreams and the shape of reality begin to rhyme. Let your body settle, your breath slow. We've wandered quite far together tonight, across curves and corners of space, through abstract folds and infinite stretches. We've looped around donuts of possibility, peeked down like cones, and tiptoed through mathematical corridors where the universe may bend, stretch, or whisper from distant dimensions. Now, we arrive at the quiet end of our journey, not with answers tied neatly in bows, but with something far more lasting, a sense of peace in not knowing everything. Because here's the gentle truth, we're not supposed to have all the answers, at least not yet, maybe not ever. But we can rest in the questions. Let them cradle us, like a hammock strung between stars. Does the universe have a shape? It might not. It might have many, depending on how you look, what you measure, and how deeply you're willing to peer into the folds of what's visible and what's merely guessed. It could be flat like an endless sheet, curved like a balloon's skin, or shaped like a four-dimensional pretzel dreamed up in a mathematician's reverie. But no matter what shape it wears, the universe never stops offering something precious. It invites us to wonder, not the frantic wonder of trying to solve a puzzle before time runs out, but the slow, spacious kind, the kind of wonder that stretches like light over billions of years, soft and continuous, asking no more of you than your quiet attention. Perhaps that's the real gift, that in a reality without edges, we are gently reminded to let go of our own, to release the need for final conclusions, sharp corners, and straight lines. To drift instead in questions that curve back into themselves, into dreams that feel almost real, and into stories that begin not with a bang, but with a breath. And maybe that's why, at the edge of sleep, our minds return to the cosmos, because both the universe and a dream share something in common. They are places where logic loosens its grip and imagination takes the lead. where things can bend and stretch and fold in impossible ways, where up doesn't have to mean up, where time may curl or pause and stillness becomes its own kind of motion. So here we are again, back where we started, though with our pockets a little fuller. What is shape, really? Can something be curved and infinite? Does space have folds we'll never feel or edges we can't detect? And in a universe without walls or boundaries, what does it mean to belong? These aren't bedtime riddles or tricks. They're invitations. You don't have to answer them. Just carry them with you, like smooth stones in your hand. Let them shift in your thoughts as you drift towards sleep. They'll be there in the morning, still waiting, still soft around the edges. And while you're settling in, if you found a bit of calm in tonight's journey, or maybe a question you'd never asked before, feel free to give this video a like. Maybe even subscribe if you'd like more quiet adventures like this. I'd love to know where you're listening from, and what time it is by you. Midnight in Madrid? 3 AM in Tokyo? Let me know. The night always feels a little closer when you realise someone else is staring up at the same sky wondering the same things. Thank you for joining me here, in this small corner of the cosmos. However far apart we may be, however differently curved the spaces between us, we shared this moment, this wondering, this quiet. And if your eyes are still open, I hope it's only because the universe was just a bit too interesting tonight. Sleep well, dream deep, and may your thoughts wander without edges.